We're just checking you can actually hear me. Test, test, test. Funktioniert? Okay, so if you're still somewhere in this building, please make your way into the main hall. I realize we had a very long social yesterday, so a few people might still be missing.
Kannst du gucken, ob die dann alle drin sind? Oder Julius, kannst du mir sagen, wann die alle... Okay. Kannst du einmal gucken, dass die alle drin sind und mir dann einfach sagen, ob noch welche kommen?
Okay, I'm getting a sign that most people are starting to be in here. Okay. Okay, yeah, so we'll just wait who's in here, that they get seated and then... Okay, so welcome to day 2. I hope you had a nice day 1 and a nice social yesterday. Let's dive right in. First, we have Martin Schedur giving us a brief illustrated history of Prometheus.
Is it working? Do you hear me? Yeah? Okay, great. Good morning, everyone. I hope you enjoyed the social event yesterday. I did. It was great. And I hope today I will have no technical difficulties like yesterday. My name is Martin Schedur, and I work at Sysnam.cz. I'm building observability stack at that company. We are so-called Czech Google, and I will like to talk or walk you through the brief history of Prometheus with images. So we will start easy in the morning, right? There are just images and some talking. So, okay. Yeah, I'll just start a timer so I have the idea. How it all started, or where you can track it back. This is the first commit in the Prometheus repository you could find. It's year 2012, and the commit message says in translation it's Zeus, cover up your skies. And it was done in SoundCloud, where the Prometheus was born actually. So there's some new kid in an observability town. It was a bit of different than the other solutions available. As I said, born in SoundCloud, was a bit similar to Borgman from Google, inspired. And the data collection approach, the pull versus push, there was lots of said about it already. So, but I'm not sure if there was any other solution except the Borgman using pull-based approach. So this is definitely a different thing about Prometheus back then. Also, the approach was open box monitoring, like you're really looking what's happening in the application. It tells you raw data, not just I'm okay, but you know what's happening in there. And the multi-dimensional model using labels, allowing you to aggregate data as you wish on the fly. And also powerful query language, PromQL, which is loved by some, hated by others, but yeah, it's powerful. I personally like it. And it tried to keep things simple. It was like single binary, and it just works. It's like, yeah, no moving parts. It was built to withstand. So as I said, it was like all-in-one solution. You have collection of data, you have visualization of the data, and alerting. This is all done in one single binary. The database is included. It's like you just run it, and that's it, right? It just works. Also, it came with some best practices, how to deploy it. So you should deploy it as close to your applications as possible, so the data collection is reliable. We already heard the highly available setup, 2 Prometheus instances next to each other, so you always deploy 2 of those. And the idea of exporters, you need the applications to support the collection of the data. And exporter is like the adapter, translator of the metrics or information about the application you are observing for the Prometheus. So those were also game changers, or the things that were really good about Prometheus. So the year 2015, and it was first public release of Prometheus. In that year also, federation was added to Prometheus, which allowed you to build a hierarchy of Prometheus instances and federate some higher level data to upper instances of your Prometheus. So this was definitely a thing that made easier or possible to aggregate data for bigger setups. And also Alert Manager was released officially. Alert Manager, if you look up the history of Alert Manager in the repository, it's interesting. At first it was just single Go file, single one. Now the code base is quite bigger. So yeah, it also came a long way. But yeah, 2015 Alert Manager was also born, and it managed the routing of your alerts from Prometheus. And the year 2016, this is actually where I hopped in. I used Prometheus since the version 1.0. Just out of curiosity, who used Prometheus before the 2.0 release in here? Okay, it's like, I know, quarter of people. That's nice. So yeah, the Prometheus, as it's now, if you start Prometheus now, it's packed up with all the nice features, all the things we heard in the previous talks. And this is really great, but it came a long way. And it wasn't always like that. It wasn't that easy. The version 1.0, that was great. There was service discovery. This is why Prometheus gained that much of traction using Kubernetes service discovery, because the number of instances you are using, the microservices approach, required like dynamic monitoring, and this service discovery of Prometheus native support for Kubernetes was the thing. So yeah, that was definitely very useful. And also, first PromCon happened in Berlin. I wasn't there, but yeah, I found out that it was 2016. So it's a few years back. And the community grew because all of these nice features that came, how it was useful, the people started to use Prometheus, and the community, the exporters, started to show up. And Prometheus got to the point of incubation in CNCF. It was actually a second project to incubate, I think, after Kubernetes. So that made it even more popular. In that year, also Prometheus Operator was first started. So I was actually surprised it's that old also. And as I said, all those things led to even more and more adoption of Prometheus. We see it in production. We used it actually from the 1.0 in production successfully. And it was like, yeah, there were some issues, but we were definitely happy about it. But there were still some things missing, or people complain about. And one of those was, for example, highly available visualization. As I mentioned, the highly available setup having 2 Prometheus instances, it's nice. The high availability is for alerting, like you take one of those instances down and the other one is still alerting, scraping the data. But the issue is, if you want to visualize data, you need to ask one or other. There's no aggregation of the data. So one way or another, if you're doing a rolling upgrade, each of the Prometheus instances will actually have like hole in the data. So this was one of the things that was missing, or people complain about it. They would like to have highly available visualization. Also, for bigger setups, there was a demand for like global view of your data. You have multiple data centers. You have 2 instances of Prometheus in each, I don't know, Kubernetes cluster, and you want to, for example, nowadays, if you are alerting on SLOs, probably you would be alerting on global data of your application, of your service, and then you need this global data view. And so you need to aggregate the data from multiple instances of Prometheus. And long-term storage, Prometheus wasn't built with that in mind. So you can find some instances running, I think there was some historical instance having like 10 years of data or something like that, but with low volume of data. But it wasn't that. I hope it didn't happen to you yesterday at the social event. So yeah, those were 3 things that were like missing, kind of, and the solution was right outside the door. And then year 2017 came, and the generic remote read and write API was added to Prometheus, which allowed us to use or build remote storages for Prometheus that were supposed to solve those issues. So yeah, in 2017, Thanos project was born, Cortex, I think, was born, and there are some other remote storages also created. So they used remote write or remote read APIs, shipping of blocks. Like the approaches were kind of different, but the integration was possible. So this started to happen. And then version 2.0 came, which was great. New TSDB came. It was like, yay, because if you use the 1.0 Prometheus, there were some issue with memory management and capacity planning with Prometheus. It was like you were tuning some flags all the time. In the documentation, there were a whole lot of text how to configure this, and on GitHub you could find lots of issues about oming Prometheus all the time. So the new TSDB came. It was completely rewritten. It was way faster. The memory was more stable. It was optimized. So that was great. There are some bugs. There's also some bugs, but yeah, that was all fixed. And then service discovery moratorium came. It was decided that the maintainers team is not possible to provide more or maintain more certain native service discovery code in Prometheus, so they froze the service discovery additions. And so in this year, after 2.0, they just stopped accepting more service discovery solutions. 2018, OpenTelemetry standard. Yeah, so the initiative was started. Like community decided there should be standardized way of exposing the metrics, because the one used of Prometheus was just proprietary for Prometheus. So based on it, the standard was created, which you can use nowadays. So it was back then. And 2019, support for subqueries came. This was also a required or long-awaited feature for some use cases. You couldn't run vector selectors on results of your function. So this was, if you wanted to do this, you needed to create recording rule, wait for the data to record, and then you could use it in PromQL. And it was really it was a lot of work, and it was slow iteration of on those things. So subqueries came, and it made it way easier, and the PromQL way variable strong query language. And vertical compaction came. Also, lots of people. Prometheus is by design, it was designed like append only database. The TSDB was designed as append only. You could have seen in other talks that we are trying to change it, or there's some people are trying still ingest data in the past, but it wasn't designed for it. So actually, vertical compaction came. You can upload some TSDB database blocks in there, and it would work. Compactor would then vertically compact the blocks. So you can upload all data. You can also nowadays, using PromTool, I think, build the data blocks using, I don't know, synthetic data or something like that. So yeah, you can nowadays backfill data in the TSDB, which can be handy. And service discovery moratorium has been lifted. Yay. Lots of new service discovery integrations are nowadays. There's something like 20 service discovery integrations, I think, added. The decision was that there has to be maintainer for each of these service discovery. It doesn't have to be maintainer Prometheus, but there has to be someone responsible for it. So yeah, but you can nowadays add your service discovery to Prometheus. And the year 2020, new React UI came. The old one using Bootstrap and jQuery was deprecated, and the new React UI was nicer. It's nicer, better. Oh, sorry. Yeah, and there are some features. It was definitely easier to add new features to this. So yeah, goodbye the old one. And 2021. Also long-awaited feature requested by users. Prometheus never provided any means of authentication. Always it was like you should put a proxy which will manage this in front of Prometheus and solve it another way. But the demand from users was so big that it was decided to add it. So support for TLS and base out was added to Prometheus. Yay. And exemplars were added. This is a nice feature allowing you to connect observability data, not just from the application metrics with logs, traces, and whatsoever. So this was plugged in, and Prometheus, yeah, the database also wasn't actually built for it, so there's some side story for it, but whatever, it works, and it's just nice and works. And agent mode was added. I said that there was uprising of remote storages. The remote write appears to be the future of shipping the data to the global solution. Actually, Cortex is using it, Thanos is using it nowadays also, Mimir is using it, and most of the remote storages are using it. So Prometheus is shipping the data using the remote write, streaming it to your global storage. And actually, it was some of the users doesn't need all the features of Prometheus, the UI, the alerting, recording rules, and whatsoever. So the agent mode to Prometheus was added, which just does the scraping, the data collection, and shipping the data somewhere. So yeah, this was added. And new PromQL editor, which is really handy, suggestion of labels, documentation of the functions. For example, if you write label replace, I personally never remember which of the argument is which. So this is really, really nice. And we are getting to 2022. First, long-term stable supported version 2.37 was released. There was a Julian talk about it in the first talk, I think, yesterday. So yeah, now you can use LTS version and you don't have to upgrade all the time. There should be backported bug fixes, etc. And PromQL prettifier formatter, quite new thing. You can now in the Prometheus UI format the query you enter in there. I hope it will get in PromTool also. And this is really, really great feature because everyone formats the PromQL different way, and sometimes it's really hard to read. So yeah, I think this is really nice feature. We also heard a talk about out-of-order ingestion. I talked about vertical compaction and backfilling. It's like you can add a whole block back in the past, but it's in the storage, and this is like a real-time ingestion. This is meant more for the remote write protocol. It came from Mimir, I think, the implementation. So it's more useful for those who are receiving the remote write. But Prometheus actually is supporting now the remote write itself, so you can use Prometheus to write to other Prometheus using remote write. So yeah, there's also use for this. And the new histograms, we already saw 2 talks about it. It's really, really something exciting, which will be great. It's already in the master. Well, everything was set, so yeah. And that's it. We just came to the present. This is all the journey Prometheus came all the way up to this point. I'm really excited about what the future will bring. Looking forward. I'm not saying what it will bring. I don't know. And at this point, I would like to thank all the maintainers and the community, because all the way Prometheus came up to this point. It's amazing. The code base is huge. The amount of work was also huge. So this is something I would like to thank you all, what you did for the Prometheus and for the community. And that's it from me. If you have any questions, I'm open for it. But yeah, that's it.
Any questions? I'm not seeing one.
It was just images, right?
Yeah, go ahead. Oh, no, we do have Julius has a question.
Okay. How did you become like this Prometheus historian? Did you do it along the way, or did you look through like all change logs over like 7-8 years to summarize?
Well, yeah, it was a lot of browsing the changelog and commit messages, some things I remembered or that, but yeah, I was speaking at other conference, or already part of the talk was given there. It was in Czech, and it was just like, I don't know, maybe it's good to sometimes think about the past and how did we get here and what led to up to this point. So yeah, and it was also fun to draw it. So. Yeah.
All right. Any more? No? Okay. Well, give it up again for Martin.
Okay. Thank you very much. Thank you.
I'm going to get up on the stage.
Yeah, actually, if you want to use, if you like any of the images, you can use it however you like. I don't mind.
Yeah, they were great pictures. Very. Did you draw them yourself?
Yeah.
Actually, now I have a question. Sorry.
Yeah, I draw all of them. So yeah.
Okay, so I'm Brian Borum, just emceeing for this morning. Great, we're ready now, I think. Yeah? Okay, so please welcome from Grafana Labs, Susanna and Marco.
Good morning. So today we're going to talk about slow queries, and in particular we would like to share with you some lessons learned building some query acceleration techniques shared between Grafana Mimir and Thanos. My name is Marco. I'm a software engineer at Grafana Labs.
Hello, my name is Susanna, also a software engineer at Grafana.
Now, this topic is not new. Actually, 3 years ago, Tom was on the stage of KubeCon, North America, to present what I think at that time was the first query acceleration technique in Cortex, which is the range query time splitting. We will share in details later on how it works. And this talk is a sort of follow-up. So, fast forwarding 3 years later, what's the current state of the query acceleration techniques we use in systems like Grafana Mimir, Thanos, and Cortex as well. Now, to understand these techniques, first of all, we have to understand why a query could be slow. And this talk is intentionally oversimplified. We just want to focus on the key concepts, and we are just going to focus on one single query. What's probably the most common query? The sum rate of a metric.
So when we run a query in Prometheus, Grafana Mimir, or Thanos, the first step is always to parse the query. And in particular, we want to find all the instant or range vector selectors. So in this case, for this query, we have the range vector selector, metric, namespace equal app. Then, given our range vector selector, we want to get our label matchers in order to find all the matching series, all the series matching these label matchers. So the way this is look up in storage is first we will look up all the series matching name equal metric, then all the series matching namespace equal app. We intersect the two sets, and the result of the intersection will be our matching series. Then, for each of our matching series, we want to fetch the samples within the query's time range. So in this case, our samples will be our data points, our value timestamp pairs, such as we have here. Once we fetch all of our samples, we will process them. So we will run the query. In this case, we will run the sum rate over all the samples of our matching series. And just a note that this process is done sequentially because the PromQL engine is single-threaded. Once the query completed, we can send the result back to the client, which can be Grafana or, for instance, the Prometheus UI.
Now, where is the time actually spent, in this process? Well, the answer is it depends. It depends on the query you run. It depends on the label matchers, whether it's a high cardinality query or not. When I talk about high cardinality query, which is something you will hear a lot here in this talk, I mean the number of the matching series of your label matchers. Like in Grafana, we consider a high cardinality query anything above 50, 100,000 matching series. And it also depends on the system you use. Like in Prometheus, all your historical data is stored on a local disk. If you run Grafana Mimir or Thanos, typically your historical data is stored in object storage, like AWS S3, which has a different latency compared to the local disk. But what we see at Grafana Labs, running Mimir across all our customers, is that roughly the 30% of the time is spent finding the series matching your label matchers and fetching the samples. By fetching the samples, I mean fetching the chunks, which are the compressed samples. And then the 70% of the time is actually spent processing these samples, like decoding the chunks, and then computing the rate and the sum. So that's why, for several optimization techniques, we actually focus more on techniques to reduce the time it takes to process the samples rather to fetch this data. I also would like to share with you what we see being the biggest factors which impact on the query execution time. So when it comes to looking up the series, which again means giving your label matches, finding the matching series, most of the time spent is a function of the query time range, whether we are querying just 1 hour, 1 day, 1 week, 1 month. The actual label matches you use, for example, if you use the not equal or not matching irregular expression, they are less performant due to how TSDB works compared to the equal or matching regular expression. And also the total number of series you have in TSDB. Why? Well, because the rule of thumb is that the more series you have, the bigger the TSDB index of each block is, and typically the bigger the TSDB is, for many label matchers, it's a little bit slower to query the index. But when it comes to fetching the actual data and processing the samples, what we see is that the time spent is mostly dependent on the actual number of matching series. Whether it's just matching one single series or 1 million series. That's completely different. And the actual number of processed sample. I would like to focus on processed sample because that's actually what we see being probably the biggest impact. What do I mean by processed sample? Let me show you through an example. We have our sum rate query, and we run this query as an instant query, which is evaluated at a given point in time. Let's say this query matches 10,000 series, and we have a time interval of 5 minutes in the query. And again, let's do another assumption, that you configure Prometheus or the agent with 30 seconds scrape interval. So over the 5-minute time interval, you have 10 samples. The total number of samples we have to fetch from the storage and process is 10,000, which is the number of series, multiplied per 10 samples per series, so 100K. Now let's run the same exact query, but as a range query. When you run this as a range query, we have to compute, basically you have to evaluate this query for every step. The step is basically, for each timestamp in output of your query. Now if you run this query over the last 6 hours in Grafana, the number of steps requested by Grafana is 1,400. So since each sample needs to be processed multiple times, basically within the time interval falling within the given step, 5-minute time interval, the total number of samples to process is actually the previous number, 100K, multiplied per the number of steps we have in the query, which is 1,400. So it's 144 million samples to process, which is way bigger than the previous one, right? Again, it's very fast to run, to process 100 million samples in PromQL, but sometimes we see some wild queries. Just as an example, if you, instead of 5 minutes, you put a bigger time interval in your range query, the number of samples to process just linearly increase. If instead of 5 minutes you put 24 hours, the number of samples to process, to iterate over and over, it's 41 billion. And what we see is that the time it takes to process the sample nearly linearly increase with the number of samples to process. So that's something to keep in mind when you're going to run your next range query.
So in highly scalable and distributed systems such as Grafana Mimir and Thanos, it's actually very easy to write high cardinality queries. So as you see, queries that can touch over billions of samples, and we as users expect these results to be quite fast. We want them fast. So in this section, we will be talking about some of the fast query performance techniques that are used in Grafana Mimir and in Thanos. So let's assume that you have a dashboard with a panel with this range query over the last 6 hours. So when the panel loads for the first time, it will execute the query, and it will have to process all the samples from the last 6 hours up until now. But then we can store this result in cache. However, due to possible delays on the remote write, we never actually cache the last 10 minutes of data. So that means that the next time the panel refreshes, we will run the query again. But this time, only the last 10 minutes of data, the samples corresponding to those 10 minutes of data are actually processed by the PromQL engine. The rest of the remaining portion of the query can actually be fetched from cache. So this means that with this technique, we are able to cache query results and get them subsequently. So for instance, if we have an incomplete cache query result, such as is this case, we just need to calculate the required partial query, in this case the last 10 minutes, and execute them separately. Then we just need to merge the result back with what's in cache and send it back to the client. So these are some of our benchmarking results that we see in Grafana Cloud for all of our customers in production. And we see that around 40% of our range queries are cacheable. Of this 40%, we have a 92% cache hit ratio with around a 5 millisecond cache lookup latency. So this technique is probably the best and the most effective optimization possible, because basically we are just fetching the results from cache. We don't need to run the code. And all the future requests will be a lot faster. But the thing is that this doesn't apply to first-time queries. So a query can only benefit from this if its time range interval was already processed by a previous query. It also requires queries to have the start and the end aligned to the step. This is because, as you know, time is a moving window, so we need to store the query results in fixed time blocks in order to increase the cacheability of the results. And this is actually the only way that we can store the results with accuracy. But if you use Grafana, you don't have to worry about this. It does automatically for you. Again, the last 10 minutes of data are never cached. This is because these are push-based systems, so it's always possible that with remote write, we don't have the most up-to-date data right now. And it only applies to range queries. So let's now assume that we have the same query, the same range query, but instead of the last 6 hours, it's spanning the last 3 days. So basically, it will have to process the samples from the last 3 days up until now. And this is a very simplified overview of the steps that we showed previously on the query execution workflow. And first, we will parse the query, then we will process the query sequentially, and we will send back the response. So we cannot, and we don't want to parallelize the first and the last steps, but we are able to parallelize the step that takes most of the time, so processing the query. And this is how we can do it. So we can split a multi-day query into multiple partial one-day queries that can be executed in parallel. So in our case, we will still parse our query, our last range query over the last 3 days. We will split it into 3 partial queries, each one with 1 day time range interval. All of these partial queries will be executed in parallel concurrently. Once they all finish, we merge their partial results into a single result, which is then sent back to the client. And as you can see here from the graph below, the execution time is reduced significantly. So some of the, again, benchmarking results that we see in Grafana Cloud is that around 10% of our range queries get split by time. Of these multi-day range queries, we see that on average the time range interval is 7 days. And we also observe the query latency reduction of 75% on multi-day range queries. So this technique, unlike with the query results caching, it works with any range query, including first-time queries. However, it only applies to queries spanning multiple split intervals. In our example, it was based on 1 day, but this is configurable. So this means that if we get a query with a time range interval of less than 1 day, we would not be able to split it. And again, it only applies to range queries. So what about instant queries? It's also very common for us to have instant queries where the instant vector selector, the time range on the instant vector selector is quite high. So in this case, the value in brackets, the 24 hours. And in here we have a slightly different query than the sum rate. We have a sum max over time, and I'll explain you why in a couple of slides. But here the process is exactly the same. So in here we will have to process the last 24-hour samples of data up until now. And we have the same sequential steps. So how can we parallelize these steps, the processing of the query sequentially? In Mimir, we recently introduced an experimental feature where we are able to split an instant query into multiple partial queries by using the offset operator. So in our case, we have the sum max over time over 24 hours, and we can split it with a split interval of 6 hours into 4 partial queries, each one composing the 6 hours, interval of 6 hours. So this means that the first, for instance, the first partial query from now, it will take into account the last 6 hours of data. The second partial query will do an offset of 6 hours and then look at those 6 hours and so on and so forth. And we can see that again, we are able to parallelize all of these partial queries in parallel, similar to what we saw on the range query with time splitting. However, there is a limitation to this feature that affects the correctness of rate, increase, and delta. And this is why we use the max over time instead of the rate. So this is because composability is not a guaranteed property in PromQL. So this means that the rate over the last 12 hours is not the same as the sum of 2 rates over the 6 hours. Because basically the two samples, the 2 intervals, the difference between the 2 intervals is not taken into account. So for instance, just to clarify in this graph, if you look into the first interval between the 0 and the 4 hours, it has a very slight increase, and the same happens between the 6 and the 12 hours. However, if you look at the sample immediately before the 6 hours and the sample immediately after the 6 hours, we see that there is a very high increase that is not taken into account when we do this sum over rate.
Now, the techniques we've seen so far are all about partitioning the workload by the time dimension. But actually, there's another dimension we can partition on. which are the series. And that's basically the main idea behind query sharding, or I think in Thanos it's called vertical query sharding. And the idea of query sharding is to partition your query by series. So we have our sum rate query. And this query can be split into multiple partial queries. In this example, 3 shards, but we can run with any number of shards. And each partial query processes a different subset of the series. Like with 3 shards, each partial query processes roughly the 33% of series each. These partial queries are, again, executed concurrently. And then we rerun an aggregation on top of the result. We keep showing, the sum rate, but this works with the sum by labels, some without labels, minimum, maximum. We also made it work with the average. We basically rewrite the average as a sum divided by count. So we slightly rewrite the query to make it work. But that's basically the main idea behind query sharding. Now, query sharding works both with instant and range queries, and we are using it in production at Grafana Cloud since several months. What we see across all our customers' queries is that 68% of the queries are actually shardable. The reason why there are some queries which are not shardable is because not every single PromQL function can be sharded. I don't know, standard deviation, we can't shard it. We can't push it down. Among the high cardinality queries which are sharded, we see a query latency reduction between 2 and 10x. And the biggest gain we see is for instant queries with large time durations in the vector selector. And the reason is basically because this technique is very effective when it comes to parallelized samples processing.
So how do we do query time splitting and query sharding come together? Well, it's actually quite simple. We can combine these 2 techniques and use them both in instant and range queries. We'll look up for the range query example, just for simplicity. So basically, we will first split our query over the range interval of 3 days. So we will split it into 3 partial queries. And then each one of these partial queries will be further split into multiple partial sharded queries. In this case, with a sharding factor of 3, we will have 3 queries for each day. So this means that in the end, we can split this query into 9 partial queries, where each one of these partial queries can be executed in parallel, and all of them will be looking into specific parts of the data.
In this talk, we just shared the key ideas of 3 main techniques we use, both in Mimir and Thanos. There are some implementation differences between the 2 projects, but the idea is shared between the 2 projects. Both projects and other projects we didn't cover use other techniques as well. I don't know, both Mimir and Thanos have several layers of caching. Thanos support downsampling as well. If you think about downsampling, it's yet another way to reduce the number of samples you have to process in your query. That's all about it. Or in Mimir, when it comes to query sharding, we also shard at the storage level. So basically, we are able to map the shards into different TSDB blocks. So when we query a given shard, all the series for that shard is in a dedicated TSDB block. This is an optional feature we have in Mimir. What's about the future? Well, both communities have a bunch of ideas. So keep watching, because Bartek and Philip will share something very cool next. I would like to share a couple of ideas that we keep thinking about in Mimir. We think that with experimental instant query result time splitting, we may be able to cache the result of the partial queries if we align them to time boundaries. Another idea we are talking since a long time, and sooner or later I will build it, is a sort of query planner. Basically, I would like to collect statistics about all the metrics we ingest and the queries we run, and then use these statistics to better plan the query execution, like how many time intervals to use, how many shards, which technique should we use in order to squeeze out the performance of the query. And that's all. I know this talk was a little bit concentrated, so if you want to get the slides and watch them again offline, there's a QR code.
So I'm guessing there will be questions. Who's one here? Okay.
Hello, thanks for the talk. I was wondering, now that we will have out-of-order sample support, will that change the caching and, yeah?
Yes, it does. Out-of-order support is a complication for caching. Right now, it's not handled very well. So the hack or the workaround is that if you configure out-of-order time window to an hour, you can configure Mimir to not cache the last hour of data. This may work if you have a short out-of-order time window, like 10 minutes, 1 hour, 2 hours maybe. Doesn't work if you want to ingest any sample with any timestamp for real. What we are brainstorming, but we haven't built yet, is a caching validation when we ingest out-of-order samples. The typical use case we see with out-of-order ingestion, at least given our customer use cases, is that the stream of out-of-order samples is not constant over the time. We're not just ingesting 1 million of out-of-order samples per second. Sometimes we have some spikes in out-of-order ingestion, and then for a few hours there's nothing ingested out-of-order. So, caching validation may work. But yeah, that's a good question. We should have included in the slides. We will update the slides. Thanks.
All right, more questions. One at the back here.
Do you think these techniques are only useful for things like Mimir, or would they be useful or possible in Prometheus itself?
Mm-hmm. I'm not part of Prometheus maintainers, so I can't speak for Prometheus. My experience with Prometheus is that so far they've been quite focused on getting Prometheus working very well, but running the query as a single core, so basically not scaling out the query execution either to multiple cores or even as a distributed system on multiple machines. The query result caching is implemented in a dedicated component, both in Cortex, Mimir, and Mimir, which is called query frontend. And the query frontend, both in Cortex and Mimir, can run as a standalone component that you can run, if you want, in front of Prometheus. So basically, you, instead of running your queries against Prometheus, you run your query against the query frontend, and then the query frontend runs the query against Prometheus, cache the result, and returns back the result. Query sharding query sharding, it's something which is deeply coupled with how both Mimir and Thanos work. So it's not something you can get out of the box from Prometheus.
Hi, thanks for the talk. My question is about this query shard factor in Mimir particularly. Can this shard factor be dynamic? Currently, can Mimir figure out based on how many workers available and figure out this shard factor dynamically? Or is it like static where you have to go and configure? Yeah.
Good question. it's dynamic. And the main reason why it's dynamic is because when you both apply the time splitting and the query sharding, you may end up with an explosion of partial queries. So think about, instead of running the last 3 days query, you run the last year query. So split 1 day queries, 365 queries. And then maybe you also shard by a factor of 8 or 16. So you have thousands of queries to run. I mean, it would be even way slower than just running the query as is without any optimization at all. So we dynamically compute the number of shards to use based on, right now, based on the time range of the query and the portion of the query which have not been cached yet. So if you run a query, I don't know, over the last 3 days, and the last 2 days of query are actually picked up from the cache, we have just run the last 1 day of query, so we can run at full parallelization with the query sharding. But if the last 3 days of queries are not cached, we reduce the number of shards for each daily query so that the total number of partial queries we run is nearly constant. However, we can do better, and that's why I'm quite keen on the query planner. Because the missing information we have right now is, before running the query, knowing how many matching series the query will have. Is it going to be an high cardinality query or a very low cardinality query? Well, unfortunately, we don't know yet. And that's why I would like to know, because we would be able to take better decisions before running the query. So, like picking up the right number of shards in order to squeeze out the best performance without overloading the system, with an overscheduling of many, many queries you just don't need.
All right, any more? Okay, I'm not seeing anyone.
Thank you. Good job.
I'm going to get up on the stage again. We're running slightly ahead of schedule, so I'm going to take a moment to thank our sponsors again. They're written on this sign here: Cloud Native Computing Foundation, Grafana Labs, Chronosphere, SIGHUP, Vaipu, and Red Hat. So thanks to the sponsors who paid to have their name there, and in turn paid for this event, the social, and lots of other things that you're enjoying. So. We're slightly ahead of time, so don't sweat it.
All right.
Anyway, I'll hand over. Yeah, you wanna swap that round, don't you?
Yeah, that's fine. That's planned. That's all good.
Anyway, I'll hand over to Bartek and Philip.
Thank you. Okay, I think we're ready. Ready? Now we're ready. Okay. Welcome everyone. Can you hear me well? Probably better with the mask. Now? Okay, sorry. Hi. Welcome everyone. We are super excited to be here. I think, it's like first in-person PromCon after COVID lockdown, so it's super amazing. And to see, all those familiar faces and new faces in the community. Today we would like to discuss, like a new open source initiative that we are kind of doing in Prometheus ecosystem. So our new open source experimental PromQL engine. What's funny is that I don't think we thought that we'll be working on this 2 months ago. So it's a very fresh idea, but we are working on it, and we are super excited about the initial results. So this is why we are here. We would love to share with you, a couple of details. First of all, why we even developing this, what's the design, how you can contribute, and generally we'll try to finish with some live demo if time will allow. Before short introduction, I have Philip with me today. No, we don't have Philip. Now we have Philip.
Yes. Hi, everyone. My name is Philip. I'm based here in Munich, actually, so it's a bit strange not to travel for a conference, but it is what it is. I currently work as a production engineer at Shopify. I'm a Thanos team member, and I also help maintain the Prometheus operator and kubestate metrics.
Thanks. My name is Bartłomiej Płotka. You can call me Bartek. I work at Red Hat. I maintain a couple of things, including Prometheus, Thanos, and lots of Golang projects. I am active in the CNCF, and I recently wrote a book. It's going to be printed like literally this week, so it's done. It's Efficient Go, about Golang and writing efficient Go code, but it's kind of like language agnostic. Lots of chapters are just about optimization, observability, and so on. So yeah, if you're interested, link is there. But we are here to talk about PromQL. So I'm kind of grateful that we are in PromCon, where I don't need to introduce this, but generally this is a Prometheus QL language, and it's everywhere, right? It's beautiful, it's powerful, it's flexible. Martin mentioned that some people like it, some people hate it. I don't think I remember anyone hate it, so if you hate it, let me know, but it's generally likable. And many vendors support that, right? And this is kind of the proof of the wide adoption. Every cloud provider, almost all of them, support some kind of like language integration, right? Including Google, Logs.io, Amazon, IBM even. And we also have trainings, right? So we have companies that specialize in training in PromQL. We have amazing cheat sheet from Julius' company, PromLabs. So if you are interested, yeah, there is a link as well. So it is everywhere, right? However, versatile language, powerful, grammar is one thing. Second thing is efficient implementation of that language. And the truth is, it wouldn't be adopted if there wouldn't be like an engine, an implementation, a storage that is quick enough to kind of show the powerfulness of this language. So we'll be talking about the implementation part. And fortunately, Prometheus comes with such efficient implementation. We usually call it PromQL engine, right? And the powerful thing about that, it's modular design. What it means that it consumes a string, which is the PromQL query, and it consumes a storage interface and performs computation, right? So it parses the query into the abstract syntax tree, AST. It selects the series from internal TSDB and performs the calculation, processes the samples, and yeah, returns the results. So string, maybe scalar, maybe vector, maybe matrix. And yeah, the powerful thing is that this is modular in a sense that it lives in Prometheus repo, but it's like a separate package. So anyone can just go to this package, import it, and have a ready engine and provide the storage, and it's that, right? So it's very powerful. So this is what we do in Thanos, right? And this is the same in Cortex and Mimir. We didn't have to rewrite everything from scratch. And it's amazing because it allows Thanos to be created really, and Cortex, because it allows the ecosystem to innovate and still have some foundations which are very tricky to reproduce. So for example, Thanos, which is like a project that scales Prometheus and federates Prometheus, we import PromQL engine directly, just we have a different storage, right? So we essentially have a storage which deduplicate because the data there, now we are talking about distributed systems, so things are replicated, sometimes 3 times, sometimes we are talking to Prometheus in HA, so 2 times. So this deduplication has to be added. And then we have remote storages. And we call them Store API because this is just gRPC API that gives you metrics. It can be anything. It can be Prometheus. We have components, Thanos receiver. We have component for Store Gateway, which is for object storage kind of data. We have rulers. We have other things. And you can integrate with your own system as well. So it's amazing because we could start very easily. And for a long time, it was good enough solution. However, as with everything, there are challenges. And this is why we are here. We would like to share with you some of those and why it triggered our ideas to improve something. So first of all, technically speaking, those challenges doesn't exist in Prometheus. In fact, it's perfect. And one, like we already have evidences of that in yesterday talks. I think Ryan mentioned about when he was querying and trying to really load test Prometheus, querying didn't even increase memory, right? So things are very, very efficient and designed for Prometheus. However, Prometheus Prometheus is pragmatic, and Prometheus project tries to evaluate the requirements, and we designed Prometheus engine to satisfy those. And the requirements are very, very specific, right? So we have in-memory calculations, so every data is in memory. If it's not in memory, it will be in memory very soon using this memory mapping feature of Linux. And yeah, so that's kind of simplified things. Another kind of requirement is that Prometheus is within, it's just a process that actually do many things. So it not only does query computation, but also scraping, also computation, or compaction, also recording rules, alerting rules, and all those things has to work. So you don't want to spend too many CPUs on querying, because you will essentially, it will be noisy neighbor for your Go routine that is scraping, which is super, super important. So that's why, the engine has the design kind of goal to maintain this isolation and not be noisy neighbor. Another thing is that the data set is like, small to medium. So we are talking about maximum 10 millions of active series, maybe, roughly within a month. Of course, you can make a bigger setup of Prometheus, but this is usually the data set Prometheus engine has to deal with. So the decisions are kind of based on that. We have PromQL engine kind of executes computation series by series, roughly. It's sequential. So by design, it should not use more than one CPU, and then everything is in memory. So those are like critical design decisions. Now, when you compare that with any other distributed system, like Thanos, Mimir, or Cortex, things are a little bit different, right? So we have data scattered around the world, sometimes in multiple regions, in object storage, in memory, in disk, and it's just more, more kind of distributed and scattered. Secondly, we have a separate process. We have this Thanos query component, which is microservice that only do PromQL computation. So there is a room for scheduling this in large clusters and actually use 100 CPUs, not only one. So why we are limiting here, our scope, our engine. Finally, or almost finally, there is a big data set, right? So we are talking about billions of active series and years of data, because we distributed this project for a reason, to be capable of scaling like that. So yeah, we are handling this kind of amount of data because, again, this is what a global system has to deal with. Finally, replication. I already mentioned we have replicated data heavily, so we need to have, engine. Ideally, engine helps with that. But the problem is it doesn't, right? As you learn in previous design goals, the PromQL engine was designed for something else. So there is theory that, and we've seen that kind of on the wild, at some point, Thanos Querier was, booming, very slow, and was the single point of failure because PromQL engine was not kind of designed for that. And, what's great is that we had a talk just before from Marco and Susanna, and they talk about exactly, the work we did within the community for the last 2 years to mitigate many of those problems, right? So, I won't be repeating this, but generally we're talking about, another component. We call it query frontend. It actually was designed by, we started in Cortex. We kind of imported that in Thanos. So, we have this horizontal query sharding, splitting by day. We have response caching. Recently, we added both Mimir and Thanos vertical query sharding on the different levels. And then we have query pushdown as well on the leaves. So we did a lot of kind of work to make things faster and better. But I want you to see the pattern, right? So we do some magic here. We do some magic here. And here we don't do magic yet, or we use alt magic. So we want to challenge that. And I think it was kind of this closed box pattern where we are maybe afraid to touch something that was so perfect, so kind of like optimized in the past. So we want to kind of address this elephant in the room, something that we rarely touch. And essentially it was scary because the amount of redesign work and kind of like complications and details. But some people are crazy, and we would try to go with you, what if we would redesign it? And in fact, we have a ready solution that works. So I will let Philip to explain that in detail.
Thanks. OK, so before we take a look at how the query engine in Prometheus and what we're doing in Talos works, we can first try to visualize what a query execution looks like. So we can first visualize, we can take this two-dimensional plane, oops, sorry, and we can visualize time series data as on this y-axis and time on the x-axis. And then the samples that we have here, they are basically observations that we either scrape or we remote write. And so when we evaluate a range query, what's going to happen is we're going to select discrete steps in this time in the range, basically. And for each of those steps, we select points that are closest to the timestamp of the step. And for each of those steps, we independently run the PromQL expression. So what the Prometheus query engine gives us back is basically discrete points, so one value for each of the steps. And something like Grafana or the Prometheus UI is going to draw a line to make that line look contiguous. But it's really like discrete steps that we're getting back, these discrete points that we're getting back. So the way that query evaluation works in Prometheus right now is so Prometheus takes the input query, which is a string, parses that into what we call a syntax tree or an abstract syntax tree. And then it will start evaluating the expression bottom up, so from the leaves going upwards. So it's first going to evaluate the selector, then do the rate, do the sum. It's going to do the right-hand side of the tree as well, and finally it's going to do the division. There are some optimizations. For example, the rate can be now pushed into the selector and stuff like that, but these are very like context-specific. They're not generic optimizations. They are like hand-coded into the engine. So if we unwrap this execution now, we see what Bartek was talking about before. Like we see this very sequential-like execution model, which also makes sense because we have a single thread at our disposal. But we also, if you look at the code and if you do some benchmarks, we notice that there's a certain buffering happening between all of these steps. So for example, if you do a sum by, the rate operation is going to buffer all of the results from the beginning of the range to the end of the range, and then pass that into the sum. So this can also lead to memory bloat from time to time and stuff like that. So the binary operator is going to buffer as well and things like that. So with this kind of constraints that we have in Prometheus and understanding how the Prometheus engine works, we've basically started a fully multi-threaded version of the PromQL engine that currently lives under the Talos community organization. And we don't want to reinvent the way that we do PromQL, but we want to redesign it so that it's multi-threaded first by design. And also, from day one, we have full compatibility with the engine API. So it's a drop-in replacement. If you're using the PromQL engine from Prometheus, you can simply swap it in. And we also have full support for the full PromQL grammar. And we do this by simply falling back to the Prometheus engine in case we don't yet have support for a certain function. So for example, right now, we cannot calculate a quantile over time. So if we detect a quantile over time in a PromQL, we'll simply instantiate or use an instance of the Prometheus engine and execute the query that way. So by doing this, we're able to kind of deliver things much in an iterative manner and also experiment with this design and see where it's going. Also, it's worth pointing out that we're not starting fully from scratch. So we've taken a look at what other databases do, how other query engines work. So there's this very influential paper from 1994. If you're interested in the topic of query engines, this is a good place to start. It kind of describes a framework that can be used for building engines in general. And this is what we've used to kind of, as a foundation, with some modifications for the Thanos engine. OK, so let's now take a deep dive and see what this thing looks like. So the fundamental building block that we have is this concept of an operator. And we see that an operator is an interface, which means that there are different types of operators in the system. And each operator has implements a next function. So the next function returns what we call a step vector or a vector. And these vectors are exactly these vertical slices that we saw in the previous slide. And so the way that we execute a query is we chain different types of operators together. And each operator calls next on its downstream operator until the downstream operator has nothing else to return. So in this particular case, the aggregate, which can be a sum or an average, is going to call next on the function, is going to call next on the selector. The selector is going to return the samples for T0. The function, if that's a rate, is going to do the rate on those samples, return that to the aggregate, which is going to maybe, if it's a sum, is going to sum everything together. And at that point, we basically have the result for T0 for that particular query. And then we simply repeat this process until we've basically gone through all steps. So to see why this model is flexible, also worth noting that because each operator implements the same interface, we can combine this operator in any different way. And this combination or this graph is what we call an execution plan. So to take a look at a specific query, again, this summary that we keep using all the time, the way that we would execute this particular query is we would create an operator for the selector. That operator is processing steps from T0 to Tn for this particular kind of sub-expression of PromQL. Then we create a rate operator. And we can immediately see that we have a pipeline-like execution model where as soon as the selector is done with processing T0, it's going to hand it off to rate. And now while rate is processing the step T0, the selector is already capable of processing T1. We can do the same for sum. So basically, while sum is working on T0, rate is working on T1, the selector is working on T2. So now if we run each of these operators in a different Go routine, we've basically parallelized the execution of the entire PromQL expression. So every sub-expression can be run in parallel, with this exception of like the few first steps, which are cold start. But keep in mind that the range query has 1,400 steps, so those first steps are not very significant. And if we make this expression more complicated, turn it into a binary expression, we can do the same thing. We basically kind of pipeline and stack operators this way. If we now run them in 7 Go routines, we basically have full parallelization. So this is how we build parallelism inside an operator, which can also this is how we build parallelism between operators. We can also have parallelism inside an operator. So we've noticed that decoding chunks, so decoding samples from chunks, doing rates, stuff like that, can be quite compute intensive. So we might want to allocate simply more CPU cores or more threads to those operations. So in this particular model, we would simply instantiate multiple instances of the rate and of the selector. And because we have a consistent interface, we can kind of interject a synthetic coalesce operator is going to merge those streams and hand the result to sum. So now we have 3 parallel rates and 1 parallel sum, so we can basically run this query in 4 Go routines. OK, so speeding up, so using multi-threading is just one way to speed things up. We can also make queries simply more optimal for execution. So we don't necessarily have to execute queries as they come in from the user. And the way that we do this, and that we've kind of seen before in the previous slides, is that we've decoupled the syntax tree from the execution model. And so now, this kind of syntax tree that we parse, we call that a logical plan. You can think of it as a logical plan or a declarative plan of what needs to be done. And so we can run multiple independent optimizers on that plan, and we only execute the optimized version. So what we have, for example, in the current implementation is if we have this particular binary expression, we see that on the left-hand side and on the right-hand side, we are selecting the same metric. So in something like Thanos or Mimir, this would cause basically 2 network calls, and it would also cause the engine to hold 2 copies of the same time series, because the right metric, so the right series, the right selector is a superset of the left one. So using an optimizer, we transform this expression into something like this. So we merge the 2 selectors into one, and then we inject, again, this synthetic operator on the left-hand side for basically, we have to do it for correctness, that's going to filter the data set in memory. So basically, we reduce memory usage because we now have only 1 copy of the data, and we also reduce latency because we don't have to do network calls. And also in the future, we are looking into adding some sort of physical optimizers. This is still up in the air. And also Marco spoke a bit about this, how they are planning to do it in Mimir. But essentially, we want to have fine-grained control of how much concurrency we want to assign to a given query. So we might want to do that based on certain statistics that we pull from storage, or based on how many other queries are currently running in the engine. So if we have a lot of queries running at the moment, maybe we want to tune that down and reduce concurrency. OK, so let's look at some benchmarks. So we kind of run a suite of benchmarks on a very regular basis. And we run that both on in a single core environment by simply setting go max prox to 1, and with basically all cores that we have on the machine. And what we see is what's interesting is that even for the single core setup, we have actually pretty good performance. We can run things faster than the Prometheus engine. Something like a sum by, for example, would run 70% faster. So we have to obviously do additional benchmarks to see if there are any cases that we're missing that might cause regressions based on how the data looks like. But so far, things are looking quite good. And on the multi-core setup, basically, we see that that gap is even wider. And I personally think, this is just my opinion, I personally think that we can even make the gap bigger, because the execution plan that we generate right now is definitely not optimal. So there's a lot of room for improvement there. We also keep track of memory. So right now, it's
Oh yeah, let's do this. Let's mirror screen.
Mirror the notes.
And because I need to mirror it anyway for demo, if this is going to happen. But it's not helping. Two good results. Nope, binding. Too good to be true.
OK. Yeah, so we keep track of memory as well. We benchmark memory usage. Right now, we're kind of satisfied with where we are, with the exception of the schizo and quantile function that we added a week ago. And there seems to be opportunity for improvement there. But other than that, things are looking quite OK. Also worth keeping in mind that if we're going to run things on multiple cores, it's hard to avoid using more memory, because each of these independent operators, shards, whatever they are going to have their own memory buffers that they use. So this is simply a trade-off that we have to accept. All right, so to summarize, we basically have a hidden flag in Thanos. It's not even experimental. It's not documented, that you can use to toggle this engine. We haven't documented it because it's such a new project. But we at Shopify, for example, have a small setup on the side that we use a Thanos query with this engine enabled, and we kind of poke around it and use it, and so far it seems to be fairly correct. And also, as I said, we have this fallback mechanism, so if we don't have support for a given function, we'll fall back to the Prometheus engine. Right now, this is what the support matrix looks like. We used to have history and quanta until yesterday when we saw history in the making. But the new native histograms that have just been released will work on adding that support there as well. And yeah, that's it. Also, I would like to say that we would not have been able to come this far without different contributors from different companies. So if you're obviously interested in this topic, interested in contributing, or even just opening issue, feel free to do that. All right. So now I hope we have time for a very quick demo.
OK. Yeah, let's do it. So actually, I want to show you the demo setup first. So roughly, the setup is like this. We have a Thanos setup, very simple one. We have 2 store gateways, which simulate maybe you have 2 object storages. And then we have 2 Thanos queryers that point to the same storage, to the same store gateways. And they don't know about each other. And one is using a PromQL engine, like the standard one. And second has this flag enabled. So we have a PromQL enabled. And this is like literally Thanos master, Thanos main branch. And I wanted to simulate like very large kind of setup. So I have those chunky blocks from, I don't know if I can tell that, but it's production. But it's like very analytic-based tenant. So they're super, there's high churn. They are like 2-week block, 8 million series. I have 4 of them. So together it's like 25 million of active series for 2 weeks. And I will perform a query against data. I will essentially query a cluster version metric, which will roughly touch, over 120,000 series, 40 million samples, and a lot of chunks. So generally, I just want you to understand that I made it, big to kind of have like a nice load test, and it's running only on my laptop, right? So let's go. I have this nice end-to-end framework that we created with Cortex team. I think Marco started that. We use that today as well. So I have my containers essentially, defined in Golang, and it's just easy to maintain. So we see things starting up. I have Prometheus just to monitor my setup, my testing setup. Let's wait for Parka, which is continuous profiling I have already in. I have tracing, of course, because how would I else debug things? And then I have 2 query UIs. So we see 2 Thanos UIs. I think I can actually make it bigger, yeah. So let's do it. So first I have old PromQL, standard PromQL. It's not old, we still use it. So let's perform this query on standard PromQL. So essentially we are performing a count over those 120 series, which is also like duplicated. So we can see it's fairly fast. It's 5 seconds now, and we can see load time here, 5 seconds. And it only produces 1 series because it's a count. But let's see what it how fast is on the enabled query. So we already say it's faster, like almost 2. Depends on the setup. It's it's not very like scientific benchmark. I'm running 1,000 things, including HDMI kind of whatever. So but you already see improvement. What's amazing, we can actually try to explain why it's so fast. So we added this kind of explanation pattern because in normal MySQL you can do that. So why not, since we are adding query planner, those phases, why not just show what's happening? So we see that it's kind of like physical plan we execute. You see that there is some aggregation going on, which is count. We have some concurrency between. This is this pipeline that Philip mentioned. We have coalesced because we want to essentially shard. My computer has 12 logical cores, so we thought that this execution plan said, okay, you have 12 logical cores. Let's do shard by 6. So you can see we essentially fetched. We fetched actually within 1 core, but then we have this selection, and then inside the engine kind of split into six shards, right? And this is already why it's faster on top of other things. Okay, let's make it more complicated. So we have this special query that that Philip mentioned, which is when you select the same metric on binary operator. Yeah, don't worry, just turn off and on, and yeah, I just perform it. I think. I hopefully click the button. No, yes. Let's try again. But luckily, it was the end of the demo anyway. Okay, let's go quickly. Yeah, I will. One button. But anyway, what is performing, hopefully, is this double query with like essentially we are selecting the same metric, right? But we are doing this in a normal standard query. You have this this query essentially selecting data twice from the machine. So we have 10 seconds on Alt. Let's see new one. Yeah, let's perform. Things are changing, so let's see. Okay, it's 3 seconds versus 10 seconds. So it's already a huge improvement. The data is exactly the same. If we explain, hopefully I will manage to do it. So we have a physical plan with before optimizations. You can see some sharding and some essentially selection here for one binary part of binary operation, and then second binary operation there is selection on other side, selecting the same metric just with additional filter at the first part. But our engine noticed that it sorted the matchers, it replaced cluster version with this filter optimization. So what we will see here in the optimized version is that we have a series selector that only fetches everything, but this is a kind of like tricky, but this is a memory address of this component in code, and you can see the memory address are the same for shards, is the same across binary operators as well, which proves we use the cached version, and then we just filter on top. We filter virtually in the engine instead of a storage, asking storage for a separate data set. And this is very visible in Jaeger UI as well, because we can kind of see what's happening. So let's take this 9 seconds. I hope this is the same query, yeah. So this is alt 9-second query apparently, and let's do yeah, many things happening, but what I want to show is essentially one select and then second select. You see 2 selection from storage happened. They were, overall concurrent, but still you use, double amount of memory, and there is some kind of work to be done on computation level to fan out, to deduplicate all of those. So it's non-trivial effort. And then this is the fast query, the new PromQL. Thanks to the optimizer, we have only one select, right? Because it merged, and it's actually very faster. And the reason is that because I'm doing on my single machine, so all those store gateways, they are noise neighbors to each other, I guess, and it's slower. So this is the power of new PromQL engine, and we just started, right? So we already have planned for like lots of amount of different optimizations that actually there are on Prometheus issues, some of them, some ideas to optimize further. So we will be only going further. And our idea for this effort is to really make sure to have community also enabled to contribute those optimizations. So all those operator kind of pattern, the optimizers, are really about to create a framework that is easy to add different optimizers for your specific environment, right? So we are enabling the gate, hopefully, of like very, very cool optimizations that will make our systems cheaper and faster, right? So that's it from us. Thank you, and we are welcome. Yeah, any questions if you have any.
Is this one? Yeah. Okay. Thank you very much. We're over time, so could maybe do one if it's a really good question.
Only good questions. Yeah. We'll filter them.
No, nobody's brave enough to claim that. All right. Well, we'll go to a break now, and back at 1:15.
Y haces el otro.
Work better. Hello. Welcome back. Thank you. So welcome back to the next segment of PromCon 2022. If everyone's ready. PromCon 2022. Okay, so please welcome Jesus and Manuel. 2022. If everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022. Hi everyone, we are really happy to be here. PromCon 2022. If everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022. As I was saying, we are really happy to be here. My name is Jesus. PromCon 2022. Yeah, we're both integration engineers at TSDB. We are also the maintainers of PromQL EU, which is an open source project. It's an open source project that gives you a curated list of Prometheus exporters that are ready to go. You go there, search for the application you want to monitor and the configuration and alerts and everything's ready. We are transitioning now to a full open source mode, so if everyone's ready, it's not complete yet. You might find some weird stuff, but we are working on it full. If everyone's ready. In this talk we want to show you guys how easy or not so difficult to secure a Prometheus server and its exporter with some things we learned from OpenShift. This year it's been a very exciting year. We've worked with a lot of OpenShift clusters, and at first we struggled of how to get information from the Prometheus exporters, how to interact with it. And it was quite challenging. So first, PromCon 2022. So we are going to talk. If everyone's ready, PromCon 2022. If everyone's ready, I mean, PromCon 2022 metrics. So it's not. If everyone's ready, account numbers or emails or passwords, right? So should we monitor PromCon 2022? Oh yes, for sure. If everyone's ready, there is a lot of public information out there. If you filter with Fabiton in Sudan or for you can find a lot of open records on the internet, nodes, portals, APIs, consoles. So just leave a query, you have the link where you can see there's a lot of hashes and you can see a lot of applications out there. Prometheus is in there. Basically you can access Prometheus consoles and of course the methods. If everyone's ready, what information can be documented? If everyone's ready, you guys use the node exporter and the send, and this goes to the exporters a lot of information. So they are giving the attackers like the perfect surface of attack. It's like they don't need to. It's a no-brainer for them to just go there and see namespaces, secret names, types of secret. If everyone's ready. So, for example, this is a few metrics. If everyone's ready, you can just with the time series. You can type secret types, you can node balancers open to the world. You can find image versions. If everyone's ready, versions. OS versions. If everyone's ready, and even the IO zone where you are working in AWS. If everyone's ready. PromCon 2022. They are going to be attackers everywhere, at least we have to give them hard time. If you give them the host and IPs, you're giving them the topology of the infrastructure, so they will need to do any scanning or discovery techniques to perform a brute force attack. So their attacks will be low profile and PromCon 2022 not trigger any alarms. If everyone's ready, also if you give them the version of your internals and those versions if everyone's ready, they might use some known vulnerabilities. If everyone's ready, of course, 2022 of registries and image versions, if everyone's ready, are public. They can try to confuse you with images. PromCon 2022, not so good intent. If everyone's ready, I hope you are at least afraid right
clusters. You can take a look at this step. From the last cube done in Valencia, in May, from two colleagues, David and Miguel, that they cover this in depth.
PromCon 2022.
So, now that we know the problem, what can we do about it?
2022. If everyone's ready. PromCon 2022.
The data normally stored in
if everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022.
A lot of consoles are
if everyone's ready. PromCon 2022.
There's a lot of
if everyone's ready.
out there.
PromCon 2022.
Let's explain how we do this in
if everyone's ready.
how I perceive
PromCon 2022.
the Prometheus environment.
If everyone's ready.
Basically, we're going to talk about
2022.
all this information,
if everyone's ready.
access control,
PromCon
plus
2022.
people back proxy. This is the first thing
if
that
everyone's ready.
Prometheus
PromCon 2022.
applies to the environment.
If everyone's ready.
To authentication
PromCon 2022.
and different Prometheus servers
if
for
everyone's
different
ready.
use cases.
PromCon 2022.
If it's an administration
if everyone's ready. PromCon 2022.
So let's talk just a little bit
everyone's
about
ready.
back really fast.
PromCon
This is related
2022.
to Kubernetes 1.6.
If everyone's ready.
Basically, who can
PromCon
access
2022.
to what resources in the cluster. So we have
if everyone's
user
ready.
accounts and service accounts.
PromCon
We have
2022.
roles and the cluster role depending if it's
everyone's
on
ready.
the space or the whole cluster.
PromCon 2022.
To bind that service account and that
everyone's
role,
ready.
we use a binding
PromCon
cluster
2022.
binding. This is an
everyone's
example
ready.
on how to apply
PromCon
the
2022.
Prometheus. Yes.
If everyone's ready.
We are going to go
PromCon
through this
2022.
fast because right now if you use
if everyone's ready. PromCon 2022.
for Prometheus,
if everyone's ready. PromCon 2022.
we just want to show you
if everyone's ready. PromCon 2022.
you need the
if everyone's ready.
what,
PromCon
which is the role,
2022.
the who, which is the service account,
if everyone's
and then we
ready.
need to associate them.
PromCon 2022.
And this is how Prometheus
if everyone's ready.
yeah, so
PromCon
basically,
2022.
here is the definition of a background.
If everyone's ready.
The
PromCon
is going
2022.
to listen that before this
if everyone's
and then
ready.
we have the upstream,
PromCon
which is the code where the
2022.
metrics is being published by the
if everyone's ready.
so it's
PromCon 2022.
Yeah. We use the
if everyone's ready.
because this is
PromCon 2022.
uses, so that's for
If everyone's ready. PromCon 2022.
Then we have the engage portal
if everyone's ready. PromCon 2022.
important because if you publish
if everyone's ready. PromCon 2022.
anyone with
if everyone's ready.
will access.
PromCon
We
2022.
only want important thing.
So with this if everyone's ready. PromCon 2022.
Because we only gave access
if everyone's ready.
So
PromCon 2022.
to get the metrics instead of
if everyone's ready.
from the squad.
PromCon
The
2022.
other thing this software
if everyone's ready.
did is
PromCon 2022.
so you can also different
if everyone's ready.
You can see
PromCon
when the
2022.
data was authenticated,
if everyone's ready.
the user was
PromCon
authenticated,
2022.
authorized, you can see
if everyone's ready.
what's happening. So it's
PromCon
really
2022.
handy when
if everyone's ready. PromCon 2022.
and this is
if everyone's ready.
you can
PromCon
configure
2022.
the job
if everyone's ready.
as we were
PromCon
configuring
2022.
to the personal export
if everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022.
Also, you need to replace the port.
If everyone's ready. PromCon 2022.
The port from
if everyone's ready.
is closed.
PromCon 2022.
Do you want to do this in action?
If everyone's ready.
One, two, I'm sorry.
PromCon 2022. If everyone's ready. 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 PromCon 2022.
And our application.
If everyone's ready. PromCon 2022. If everyone's ready. PromCon 2022. If everyone's ready, 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 PromCon 2022.
So now, what else?
Yeah, let's secure the Prometheus console, because we saw that we can secure these porters, but now we have the API and the console, which is a place where you can, any user can retrieve the metrics easily.
Yes. Even if you are exposing your Prometheus console internally to your organization, you might not want any person in your organization to have access. So maybe you want to have some can do this easily with OAuth. Everyone knows OAuth. Basically, is like the standard authorization. It's an open source authorization protocol, and it's like an open standard. Basically, in order to access to a resource, you have to have a token. In order to get that token, you need to log in against the OAuth server. There are a lot of ways to do this in Kubernetes. There are already ways to do this. There are software that you can deploy directly that does it for you. But we did it this way to see all the architecture that you need.
Yeah, we are using Gmail Auth as the provider that is going to authenticate us. So basically, we deploy the Auth 2, which is a proxy, as well as we saw with the airbag. So the address is the 4180, and we have the callback, which the petition will come to us.
The 4180 is where the OAuth server is working.
Mm-hmm.
You have to configure it. It depends on the provider you're using. In Gmail, you need to configure this. And then you need a service, because you're going to have an ingress. And this is how you expose it, your console, with that name, with that DNS, test.myprometheus.com, and you associate it with your Prometheus server service. And then you create another ingress for the OAuth, the URL that your OAuth uses.
Mm-hmm.
So basically, you all know how this works, but so what I'm talking about is this.
So we are accessing here to a domain we've got, so to the console, and we'll see that we first have to authorize and authenticate with Gmail. So, well, don't use the Gmail because it belongs to me. And then we put the password, we accept our token in our mobile, and then we get to the console. So we can filter what department can access to the console.
With group of users.
With group of users. So we can use Azure services, GitHub, Gmail, so any provider on the internet.
Yeah. This way you use Prometheus just for what it's intended to be used, to metrics and observability. So the other thing that OpenShift does, which came to our attention, is OpenShift differentiates the system scope from the user scope. So this is another way of isolating the users from the administrative tasks. So you can have a Prometheus server, which by default in OpenShift is in the OpenShift monitoring project or namespace for the API server, the operator, the etcd, node exporter, blah, blah, and this is one Prometheus server. But you can't configure jobs, custom jobs in that server. If you want to do, you should not. You can, yeah, you should not. You can do it. We did it, but you shouldn't. The suggested way of doing it is by creating another Prometheus server in another namespace just for the users, for your business logic, your exporters, wherever. And this way you are isolating users from administrators. Obviously, you can see there are shared resources between them. You can have a shared alert manager or a Thanos query or things that are in the middle. But the metrics are in separated databases. So let's
Yes, some best practice summary. Always use the Helm charts, the official Helm charts, because it includes the airbag. It's straightforward, and you have different flavors. You can deploy just the server with the alert manager. You can deploy all the operators. And
today is a no-brainer, right? You want to install Prometheus, it's just a point of just a couple of commands. And you should use TLS at least. OAuth isn't as complicated as some people think. It's just a couple of configuration. And with Cube airbag proxy, you don't need to configure all those authorization and authentication manually. So this is a very nice way of securing your exporters. Your exporters, I mean the exporters you are using, because sometimes you don't know who those exporters are. And of course, it isn't a good idea to expose your API, your console to the internet, because bad people with Sodan can find you. So that's all. Basically, Prometheus have sensible information. We need to secure it, and airbag is not that difficult as it sounds. It's just who can do this, who, and how we can relate to them. So that's all. That's what we learned. I hope it was useful.
Thank you, everyone.
Thank you.
Does anyone have any questions? Okay, going once, going twice. All right, let's, does anyone know where the next speaker is? Thank you, anyway.
Thank you.
Oh, okay. I'll relay that because it was shouted, not amplified. The next speaker could not be here in person. We have it on video, and it will appear shortly.
Hi there. I'm very sorry that I can't attend the meeting in person, but I hope that you like this talk. My name is Xintao. You can find me in Twitter and GitHub using this ID. And I'm an SRE. As an SRE, I receive a lot of alerts, and I don't like them. So today we will going to talk about how can we make them less annoying. We will talk about how to set up alert rules with confidence and how to fire alerts with more information and how to review alerts. Let's dive into the first part, how to set up alert rules with confidence. If you have ever set up alert rules, I think you will ask those questions to yourself. For example, did I use the syntax rules correctly? You don't want to break the whole alert rules configuration and just missing a column in the YAML. And is this threshold reasonable? How many times will my alert be fired every day? Will somebody be spammed by my alerts if the threshold was too low, or to be more worse, the alerts won't be fired if there's something going wrong because the threshold was too high? And who will receive this alert? And what if all of my alerts are all set, but later someone breaks them, just changing some labels and or thresholds? The answer to those questions is CI. Before we dive into CI, I need to explain that we use GitOps to manage all of our alert rules. The GitOps means that we put everything into a Git repository, everything about the monitoring observability. For example, the targets, the service discovery for Prometheus, and the alert rules, the alert routing in Alert Manager. The good thing about GitOps is that everything is in Git. You can check the changes in Git commit history. You can use Git clean command. And the revert rollback is very easy. And you can review the changes like you're reviewing the code. Everybody is very familiar with the pull request UI and the merge request UI. And CM will test everything for you. That's the main part of our today's topic. And there is no magic under the hood. Everything is in the code repository. If you want to know how is something works, you can just check the code. And in Git, you can use your favorite editor to edit everything. Yes, I mean Vim. The downside of using Git using GitOps is it's not very user friendly as web UI. Some company has a wrapper around the alerting rules. It's a web UI. You can just creating or editing existing alert rules by click some button, input some fields in the form, then the system will converting the web UI into the alerting rules. But I always found that in the end, you need to how did the system work? How do they transform the input into the alert rules so that you can use the system very well? So in a way, it's not that user-friendly. And we can see that GitOps is also user-friendly. It's just very picky about who its friends. Let's see how the UI can, how the CI can help you in setting up alerts. Let's talk about the first question. Did I use the syntax rules correctly? The answer to this question is the prom tool. Prom tool is the built-in tool in Prometheus. You can use the command prom tool check rules to check if all of the syntax is correct. And you can add this command into the CI. It works like this. Every time somebody opens a merge request, then the CI will run this command. If the syntax is correct, then the CI will successfully ended, return the code 0. And if there is something wrong, the CI will fail. And the prom tool will tell you which line has which issue. It's the error message is very explicit. You can also test the syntax of alert manager using the AM tool check config. It works the same. And a more complicated example is this question: is this threshold reasonable, and how many times will my alerts be fired? If the threshold is too low, then there will be too many noises. If the threshold is too high, then we won't be noted if there is something going wrong. My idea is that when we can use the real world data to evaluate the alert rules, so it's implemented like this. When a merge request is open, this CI job will be triggered. Then the CI will firstly load in the alert rules from the source branch, which we made the changes. And then it will switch to the target branch with normally main branch and load the alert rules again. Then it has the two sets of alert rules. Then it can find the changed rules. Once it finds the changed rules, it will save the changed rules into a new Prometheus alert rules file, which only contains the changed rules. And then it will replay the changed rules against the production Prometheus. And then it will know that the changed rules, how many times will be those rules be fired alerts. Then it will report the result in the merge request by comment. It works like the code coverage bot. When you submit a pull request on GitHub, some projects, there will be a code coverage bot that seeing how many lines of code are changing and how many of them are covered by unit tests, right? It works the same way. Basically, whenever a rules was changed, you can see the past 7 days fire history. We found that the 7 days is normally enough. This pipeline is very easy to implement. Only one of the difficulty is the replaying part. For the replay, it works like this. It has 3 steps. The first step, read the history data from production Prometheus, and then evaluate the recording rules or alert rules against the real data, and then save the results for as new metrics. This feature in somewhere called rules backfilling. Here we focus on the alert rules. For alert rules replaying, the generated result was alerts with the labels as new metrics. If the alert should be fired, then the value is 1. If the alert was not being fired, and then the result will be null. So once the new generated alerts were being saved to temporary Prometheus in CI, and then we will read the result and then generate the report. There are 2 tools implemented this already. One is PromUtil script by TSDB. It's only 200 lines of code. It's very easy to understand. And another is VM alert by Victor Metrics. It's supported rules backfilling by default. This is also a very useful tool. The generated report is something like this. There are 3 columns in our implementation. The first column is find times, the first column, the first column is the labels come with the alerts. And the second column is the firing times when this alert should be was being fired. And the third column is where will this alert be sent to? We have the third column information using alert manager. Let's see how can we do this. Okay, there is a tool called AM tool that comes with alert manager, and it has a feature called root test. You can use it like this: AM tool dash alert manager UIL and configure root test, and then you put all of the labels that you get from the alert replay. You can see that you need alert manager UIL. We test this basically using the same way that for the alert replay. We start a temporary alert manager using the alert manager configuration in Git repository, and we tested the generated alerts with labels against this alert manager. And the second line is the output of the AM tool. It will tell you which channels will receive those alerts. Okay, the last but not least question: what if someone breaks your alert? The answer to this question is unit test. Unit test for Prometheus is like the unit test for code. Basically, you have alert rules, right? And you need to write the simulated data to test your rules. You write your data, and the alert should be fired or not, and then you use PromTool again. PromTool test rules. If the alert rules fired your alerts as expected, then the unit test will be success. Otherwise, it will fail. Okay, finally, we have tested everything we can when a new change is made. And if everything works as expected, the CI will be green. And then we can review by peers. We can comment, communicate in the comment. If everything is okay, then we merge the change. And the GitLab or GitHub CD will push the changes into production environment, and the alert rules will take effect. Then the next step is receiving the alerts or firing alerts. Imagine this: when you see this alert, what do you know? What's the question do you know the most? For me, when I see this text, I will wonder how bad is it, right? How high is the CPU usage now? I think that's the first question comes to everyone on call. If you see this message as an example, if you see this message, this picture, you will know that in our situation, I will know that our stress test team is running the stress test. They want to test the system's capacity using generated fake request. If the system is okay with the current QPS, they will increase the QPS until reach the system's capacity. So the stress test, the test team will focus on the dashboard closely, so they won't overloading the system. So if our SRE see the picture like this, the CPU increasing step by step, then normally it's created by a stress test team. You can verify it in the stress test platform, but usually this is the case. And there are other patterns of the known issues. For example, the first is the stress test, and the second one is not typical on CPU usage, but it's very typical on memory. Normally, when we do when after a release or after a certain bug being triggered, the memory will increasing slowly and reach the threshold and finally be killed by our OM killer. Normally, there is there is a memory leak. We need to troubleshoot bug. The third image is either a DDoS attack or we have a real user traffic. Because some big seal, yeah, either situation we need to check it immediately. And the fourth image showing that the capacity is being reached. The QPS or CPU usage was reaching the threshold time by time. We need to scale up our system. So you can see that the alert chart is very useful when we receive the alerts, right? Let's have it. How can we get the image? It's very straightforward. You just query the metrics from the data source, from Grafana or Prometheus directly, and then you render the image, and then you send the alert with the image, right? The problem with this is when Prometheus evaluates your alert rules, if the result is null, then it means that everything is okay. Prometheus won't fire an alert. If the result is not null, then the alert should be fired. So if you just render the image using the alert rules from PromQL, you will get the image like this. The line sometimes has the line, sometimes it's blank. It looks like missing. This actually is not the worst image. Normally, the real alert rules, if you render it, it will be blank in the most part of the image, and it's only show very small part of the line when the alert being triggered, right? So what we need to do is that we split the PromQL alert rules into two parts. The one part is the expression. The second part is the threshold. So when we render this image, you can see the line and you can see the threshold, and you can see when the line and the threshold crossed. So I wrote a tool that called PromQL PY. It can pass the PromQL into two parts, the expression and the threshold. And it can also pass the AND or operator. If the alert rules had AND, you can render it into two parts within two images. And then I wrote another tool called Matrix Render. Basically, it's a HTTP service, and you can get the rendered image using the HTTP URL, and you pass the expression, the alert file time in the URL, and the data source name in the URL. Then you will get the image. Then you can add this image into your alert template. So that when alert file, it will looks like this. Compared to our previous plain text alert, you will find this alert is much helpful. Okay, last but not least part, review alert with confidence. If we don't have the review process, we will have more and more alerts, and some of them will have too many noises, and the SRE will get familiar with the alerts. When we receive them, they will think, oh, that's okay, because it's not very severe, and you can just ignore this alert. You don't want the alert bothers everybody time by time, and if alert can be ignored, it shouldn't be fired at the first place, right? And so that we need to review the alerts. How can we do this? We need to have the information, right? We do this by alert manager. We actually create a reaction center, a system. Alert manager, we configure a route at the very beginning in alert manager. When an alert should be fired, alert manager send the alert using webhook to our reaction center first. Then alert manager will send alert to other channels based on the routing configuration. Our SRE or people on call receive this alert. It can interact the alert with in the reaction center with the other colleagues. We can acknowledge the alerts. We can comment on the alerts. We can make more reactions like mute the alerts or create Jira ticket to follow up the improvements. And when the resolved message, when some of the instance was resolved or fully resolved, the alert manager will send more information using this webhook, and the reaction center will append the timeline. And once we have those information, we can have the summary, the report of the MTTR of the alert acknowledge time and alert recover time. So we can, and how many of the alerts were marked as noise, false alarm, and how many of them are real instant, so that we can tune our alert rules. The routing configuration that I mentioned is something like this. You just put the reaction system webhook into the first place, and you have to set the continue to true. So alert rules will continue to send the alert into other channels. That's the web UI of our reaction center. You can see people and the alert manager can interact with the event. Okay, that's all I want to share regarding the alert path. Thank you.
All right. Is this on? Hello? Yes, okay, great. Thanks very much. Zintao is not online right now, so no Q&A for that talk. Lunch is next. We're a little bit early. We'll pick up the timetable as documented, so 1/4 is when we're back for the next talk. Thank you very much.
Okay. Okay, cool, I'm live. All right, so next up, we've got Chris, who I have the pleasure of maintaining remote write with. And Chris is going to talk about custom data sources.
Thank you for the introduction, Callum. So today I'm talking about using PromQL for custom data sources. We've already had a couple of great talks about PromQL and queries this morning. This is looking a bit more at the other side of, instead of improving samples and that, we're actually going to look at how we can get data back from any sort of data source you want and put it in a format that is available for PromQL to query. So first off, a bit about me. I'm a Prometheus maintainer for about 3 years now, mainly focusing on remote write. So the query side of Prometheus is a bit newer for me, and I had a lot of fun learning about it. I'm also working at Grafana Labs on some of our machine learning projects. And when I'm not at my desk, you can find me out in the mountains of my home doing skiing, hopefully very soon again, climbing, hiking, things like that. So what are some of the problems and motivation that I have for using PromQL? Like at least 2 of you that I heard this morning, I enjoy PromQL. I'm also very familiar with it. I use it every single day for running all of our systems. And I want to use it to also explore data in other systems. I'll show a quick demo in a little bit where I can look at some of my Strava activity data with PromQL and just explore different visualizations that way. We also, as part of the machine learning team, we wanted the ability to use PromQL to actually query predictions into the future, very similar to what Andrew at GitLab was doing yesterday. We want to be able to display that data with PromQL. And we just found a lack of customizability in how we were managing to get data into existing Prometheus, into Mimir, into Thanos, anything like that. And finally, some of my motivation is just for fun and learning. I like playing around with new tech, and maybe there's cool things that you all want to visualize with PromQL as well. So just a little bit about what are the sources of data that you can use to query with Prometheus today. First is the most common, direct instrumentation or an exporter. Prometheus comes along, scrapes that data. It works for almost all of Prometheus's core use cases. But you can actually also do custom data with remote read. Remote read is typically used to retrieve data that was remote written to an external system for long-term storage or something like that. But you don't need to do that first. You can just implement a remote read server that returns whatever you want. And that can be used to do very interesting things like provide data that is then used in joins, have custom data, things like that. But there's some downsides there. For one, it doesn't support the really nice autocomplete features that require the label names and label values support. And it also still requires a Prometheus instance to be running, which for something like my Strava data, I don't really need that in Prometheus at all. So an idea I started experimenting with was actually just creating a dedicated service that still uses the Prometheus API and the Prometheus code base, but plugs in a different backend for the storage of whatever you want it to be. So just a very brief look at what that is you can still use Grafana, the Prometheus UI, whatever you want. That will be connected to just a custom PromQL server, and that will query your backend data source. In this case, I will show a quick example of a Strava data. So let's exit out of that. Make that a bit bigger. So here's just a running local Grafana instance. All I've got in it is a Prometheus data source that I've called StravaQL. I can hop over to Explore and look at the different metrics that I've implemented so far. So here's a few of them. Let's take a look at Strava elevation gain meters total, so how much elevation I'm climbing. And let's look at that across just a week. So how much elevation am I climbing in a week over the last year? Cool. Wait. wait a few seconds, and you get a response back. So this is what a example response from my little Strava demo is. It splits it up by the different sports that Strava allows. You can see I did a lot of climbing kind of last spring and winter, but that's actually alpine skiing, so that's really just riding a lift. It's not that interesting. So let's actually filter that all out. As you can see, type ahead working as you would expect. And here you are with the remaining. We could maybe sum across that and get an idea of, and I can just really quickly analyze how my training, how my activities are going. I think this is a little interesting because not climbing a whole lot during the colder months, and then as all the snow melted out in Colorado where I live, really got into those higher peaks and doing more adventures over the summer. So that's just kind of interesting to see for me. You can also do some interesting things with like offset queries, where I can suddenly compare last year to this year and how much I've been doing activities this year versus last year. So like this summer, greens this year, yellows last year. I was struggling with some injuries, not quite as much volume, but started doing better and have caught up recently. It's just kind of fun things to track. So that's a quick little demo. And then, so how can you do this? How can you do this for your data? It's really not that hard, and it was really fun to see just how far these interfaces have come along, that you can implement whatever storage querier interfaces you want, and that you have to implement that. You have to implement some iterators that I'll go over pretty shortly, and then you just need to create a server using v1.newAPI call in Prometheus. That call does take about 15 different arguments, but most of them can just be nil or little dummies. I basically copy and paste it from somewhere each time I create a new one. So let's start with how do you actually create these queriers? Something interesting about the PromQL API is you actually create a new querier for every single request. And the querier gets created from a few different things, a context, and a min time and a max time for your query, so you know what sort of data ranges you need to be fetching data for. And it also gives you a great time to inject any sort of custom components you want, so like a Strava client, gRPC clients, anything like that. And the context gives you an opportunity to put in values for, say, a customer tenant or different request headers, something like that that is request specific with a middleware. Once you have a querier, you need to implement these 4 functions on that querier at a minimum. So we've got select, which is doing the core of the work, and that is actually pulling the data, the samples back and transforming them into series. And we'll go further into that soon. And then there's label names and label values implementations that I mentioned. You can just return nil, nil, nil for each of them, but I really like having type ahead, so having at least some knowledge in each of those is super helpful. And close is self-explanatory. It cleans up resources when you're done. So let's take a look a bit more at select. So this is kind of a common pattern I have found when I've been making these custom PromQL servers, is that I will take select, and it comes with matchers. And the first thing I've commonly done is just parsing out the name and requiring a metric name to be set. Prometheus doesn't strictly need a metric name in every query, which is very powerful, but a lot of other backend data sources, you'd be just fetching far, far too much data if you tried to effectively do a select everything. So I'll commonly require a metric name, and if one isn't present, you can return an error series set, which will return a 422. I believe that's unprocessable entity to the user. And it also means you probably shouldn't use an error series set for something like a intermittent 500 that gets returned. The best way I've found to handle that is actually to panic and then recover the panic in a middleware to return a 500 from PromQL. So once you get a metric name, I'll usually split up and look and do different logic for each case. So the quick Strava sample is for something like Strava activities total. I just need to fetch all the activities for a user for the given interval and matchers. But for something like moving duration, I actually have to figure out, I have to sum up all of the different times I've spent on each of those activities. And then finally, in the case that nothing matched, you can imagine maybe this is also a map or something like that, you can return an empty series set that is also implemented for us. And that's really useful to keep the same behavior in Prometheus, where if you put in a query that doesn't return any results, you don't get an error back from Prometheus, you just get no results. So empty series set, very helpful. So let's take a bit more of a look into what the, first off, select hints. These are really actually quite useful that I didn't show on the last slide, but it allows you some really fine-tuned control over making queries correct or more efficient. So these select hints also come in for every select, and they contain things like the start and end if they're different from the overall query, as well as the step, which can be used for how frequently you need to look at data. The function, is this a rate or an increase or an average over time? You might want to aggregate your data differently for each of those. So this is just a really good thing to know about. And then finally, here we have what a series set looks like. So you saw we're just returning series sets from select, and they're iterators across series, which are just defined as a label set and another iterator of samples. And you'll see that as a common pattern where all of these are iterators. So here is also the iterator for samples. We'll take a look at this a little bit more in detail, but some things to notice is that we have both next and seek, which you're only ever having to look forward in time, which is nice. And then the at function, the at is just returning a sample timestamp and a sample value. It's kind of a lot to implement though, and Prometheus comes with yet another helper function, which is this new list series iterator, which allows you to just create a slice of samples and return that, and it does all of the iterator logic for you, which for these examples like Strava is much easier than implementing the iterator I found. So here's the code that I have from that low Strava sample, and this is also on my GitHub, so I'll have a link at the end. But what I'm doing is looking across all the timestamps in my select statement, and then finding all of the activities that are before that timestamp, counting them up, and for each timestamp appending that value. And we just go through for each timestamp, do that, and that's really how all of those were implemented. But instead of plus plus, I might do plus equals for every single activity's moving duration or something like that. But there are times where you want to go back, I'll just go back to this chunk iterator side, where you do actually want to completely implement this iterator. And those are things where you could say need to fetch a lot of data back from remote storage. You might want to do that in a lazy way, or it might be too memory intensive to store all of the external systems data in one place. At that point, this next and these seek calls are very important, and you can get some good performance improvements by actually implementing the iterator. And then just kind of some final notes of different gotchas that I've found if you are going and creating your own PromQL data sources. So the first one is staleness handling. Just kind of curious, how many of you have ran across staleness issues in Prometheus before? At least, honestly, like 10%. That's more than I expected. So by default, Prometheus will look back over the last 5 minutes and only the last 5 minutes for any samples. For Prometheus use cases that are scraping every 15 seconds to maybe every 1 minute, that works really well. But if I'm pulling data back from a system that only reports data once an hour, unless your query happened to align to the timestamp within 5 minutes of that hour resolution, you just end up with no data back. So you have a couple options there. You either have to align all of that sparse data to your query, or you have to create some sort of interpolation so that you return at least a data point every 5 minutes, maybe even more frequently than that, depending on the functions being used for your queries. And you also will want to keep in mind that stale nan, there's a specific not a number value that exists in Prometheus that will mark the end of a series. And if you're pulling data back from an external system, that system's not going to know about this, and if you know a series ended, be sure to inject that stale nan yourself. And then it's very common to have just some sort of caching layer in addition. So that's something like, for the Strava example, I'm very likely to change data over the last week. I might be on a backpacking trip and just uploaded my activities a week later. And this is one of the reasons I can't just write a Strava exporter that returns all of the data at time right now is, well, that activity I did 3 days ago, I wanted those metrics from 3 days ago instead. But I don't want to have to refetch every activity from the beginning of time in Strava. So in that case, maybe caching data starting a month ago would make a lot of sense. And then finally, one other thing I really like about these custom PromQL servers I've written is that I can try out new query improvements, new features. The Thanos query engine is actually something I've been trying out on the one of these I've written at Grafana to get some really nice query improvements for our customers. So those are just some other cool things that you get to test out by doing some custom PromQL servers. And that's all that I have a presentation for. You can find the code for this Strava server and GitHub, and any questions.
So cool. On the staleness handling for sparse data, I mean, you're probably aware of the look-back delta that you can set, but was it not what you were looking for there? Like in the PromQL engine, you can just configure the look-back delta to be arbitrarily large.
Yes, that is, I can hop over to that actually, I believe. So you can configure the query look-back delta kind of based on your system. And that is one option that you can do, unless it changes depending on the query. That is a value for the entire server, and you can't customize it per query. So sometimes I still had to align things manually or interpolate. But good point. You could create a new engine every time, but when you actually go to define, like, you'd have to create a new API every time, I think.
Yeah. Any other questions?
You said sometimes you have to reconstruct a counter from incremental data. Say you walked 500 miles and then you walked 500 more. How do you safely set like a starting point for that counter?
Yes, so that is a great question. There are kind of two ways to do that. In my super basic Strava, I just set it at the beginning of time each time. But that is something you can do with the query hints. If you know that you're putting in that this is going to be surrounded by a rate or an increase, you would only have to construct that counter from the beginning of basically the query min time. And that's a great optimization rather than having to, I mean, I think I have 6 years of data in Strava right now. I might only have to fetch a year of data instead of 6 years if I know it happens to be surrounded by an increase.
Anyone else? Going once, twice? No? Okay, cool. Thank you, Chris.
Right. Thank you, everyone.
All right, next up we have Muad and Maciej, and they're talking about monitoring as a service.
You have to set up the microphones also.
Cool. Hello, everyone. Thanks for coming to our talk. Today, we're going to be talking about mass for the masses. So building your own monitoring as a service, why you would do it, how you would go about doing it.
So hey, everyone. My name is Maciej. I'm working as a software engineer at Red Hat at the OpenShift monitoring team. I'm also Thanos maintainer, observatory maintainer. That's about it.
Cool. My name's Moad. That's my face. That's my face. I work at Red Hat with Maciej as well, and I focus primarily on what's called the Red Hat Observability Service, which is how we gather a lot of telemetry for OpenShift from tens of thousands of clusters that are running.
We also wanted to give a shout out to our colleague Saswata, who was supposed to be with us. He was supposed to talk with me. He was also helping us with the presentation and giving us feedback. So if you're watching, Saswata, hi.
Yeah, he's alive. He just couldn't make it to Germany. Cool. So context. So what is monitoring as a service? It's pretty straightforward. It means you have a third-party service. You might own it, you might not, that you send metrics to. Why would you need that? Kind of the challenges around multi-tenancy if you're having multiple people use this. And then how to migrate to using mass. What are some projects in open source that you could use? What are some commercial products you can use? And how much will it cost you? I think that's an important question for a lot of people. Observability kind of exists in the space where everybody wants a lot of it, but nobody wants to pay for it. So that's always a sensitive topic when it comes to metrics. Before we start, though, I want to kind of get an impression of where everyone is in this kind of journey, if they are using monitoring as a service or not. How many people use Prometheus in production? Just a show of hands. So most people, that's good. At PromCon, most people use Prometheus. That's great. How many of those people use a third-party monitoring as a service? So a handful are smashing. That's much less than I expected. And how many of those people who put their hands up use a commercial one? So a third party. Okay, so about half of the people that put their hands up there. That's quite interesting. So before we go into why you might need monitoring as a service, let's just look at a typical use case. You have a Kubernetes cluster running somewhere. You have some pods in a namespace. This is a simplified diagram. And then you have a Prometheus that's scraping those pods. If you want to query those metrics, you access the Prometheus directly through the HTTP API, query range, everything else works fine. You can add it as a data source, and it's great. So there are some problems with that approach. You have a central point of failure for your metrics. If something happens to your Prometheus, you can't get your metrics, you can't run alerts, etc. So the kind of typical way that you would run it in a cluster is as a HA pair. As mentioned, that there are issues with high availability, which is that both of them are scraping the same targets, as was mentioned yesterday. And then you just query one of them. And then if that one's down, you query the other one, or you set them both up with some kind of deduplication. So let's extend that use case. I've been building a service in a cluster. I'm monitoring it with Prometheus. Now I want to run it in different environments, maybe in different regions across the world. Now I have this problem of lots of clusters with lots of Promethei in them, and then me having to add data sources effectively for each one in Grafana, or having to go to the UI, the Prometheus UI for each one individually to query metrics for it. This isn't great. Whoops. This isn't great because it's quite laborious. If you imagine I have not 4 clusters, but 100 clusters or 10 clusters, this quickly becomes untenable. So really, a lot of monitoring as a service providers, projects, kind of invert the pull-based model. The talk before mine touched a little bit on remote write. It's awesome that you were working on it. But remote write's really cool. It lets you push metrics instead of pulling them. So you add some configuration to your Prometheus, you give it a target, maybe you give it a token if it's authenticated or not, and then you can just push your metrics there. And now you have all of your metrics persisted in one place. You can correlate these metrics quite easily. You can access them even if the source cluster is inaccessible. Maybe there's an AZ outage or something. But there are some problems with this approach, which is we're kind of making an assumption that everyone who's consuming this metric, or these metrics, sorry, are from the same group of people, group of users. So they're not isolated by consumer or producer. And now you've introduced this shared bit of monitoring infrastructure if you're running it yourself or if you're paying someone to run it for you, that has to handle all of these different potential tenants and how they interact with each other and where their data lives. So that's where this kind of tenant model comes in. This is the de facto way that a lot of these projects address this, especially within the Prometheus space. And that's where you identify your producers when they write metrics. So when they write metrics, they say, I belong to a particular tenant, and these metrics belong to that tenant. And then when your users come along, they'll use credentials for a particular tenant and access metrics just for that tenant. So that kind of solves the problem of multi-tenancy in inverted commas, where you have all of the metrics go to one place, but the tenants themselves are mutually exclusive, and they won't be sharing metrics. So Matty is going to talk a bit about the Prometheus data model.
So how can we enable this on the Prometheus data model level? Let's take a quick look. So as most of you are familiar, we're dealing primarily with time series. So where on one end we have metric name and a set of labels, right? And on the other end we have samples, which consist of timestamps and particular values. So how can we make this, how can we enable multi-tenancy based on this data model? It's rather quite simple. We can use labels to do this. So we can add a special label. For example, we can call this a tenant ID, which will specify the ID of the tenant that this data belongs to, and then it's just up to us to make sure that we inject this label upon ingestion of the data, and that we enforce this label when our tenants are querying the data. So in short, this is how we can do it on the data model level. So now, cool. Now we talk a little bit about what's MAS, what's high availability setup, a little bit about the Prometheus data model. But there's more to this topic. And to kind of illustrate, we'll start by setting up our own imaginary monitoring service. And we imagine that we start with kind of a conventional setup. So we naively set up our solution, whether it's like a vanilla Prometheus, or we use one of the high availability offerings, Thanos, Cortex, Mimir. We put some labels on the tenant's data, and now we declare that we're open for business. And soon enough, more and more people will hear about our awesome service within our organization, and they will start to ask for access. So naturally, we let them all in. And finally, you will find yourself in a situation like this, where it's starting to look a bit too crowded. And we start to discover some facts about our tenants. We notice, for example, this tenant in blue is a particularly big tenant, and they are sending us all the data they have, and they're hogging a large portion of the resources for themselves. Another tenant, the one in the yellow, got somehow confused. They misconfigured their Prometheus, and they are now sending a barrage of requests to our service all the time, effectively trying to DDoS us. In the green color, we have now a very important tenant, and this tenant represents our most profitable service. But now they're reporting to us they are unable to debug and monitor their applications because our service is simply refusing to serve their queries, so they are kind of blind to their deployments now. And in the red, we've seen that's not even our tenant or user. It's somehow a malicious actor that got into our internal network, and they are now spying on our infrastructure. They are reading our metrics without us knowing it. So we can declare that our service has officially collapsed. Whatever service level objectives we have set for ourselves, we cannot achieve them in this way. So as we demonstrated on this small hypothetical example, running a multi-tenanted monitoring service is not without a challenge. And the challenge is not only present in the dimensions you usually think about, like resource usage and scalability, but also in the organizational aspects. It prompts us to start dealing with questions such as who are our tenants, what are they doing, and how much data they are writing to us and reading from us. Letting everyone do what they want is obviously untenable, and we need some measures to make sure our tenants can play nicely and that we can attain the service goals we set for ourselves. As opposed to the traditional Prometheus setup where usually one entity is responsible for production and ingestion of the metrics, you as a service operator cannot presume any control over your clients. They must start sending you whatever and whenever, and you need to be prepared to deal with this. So implementing multi-tenancy measures is then what will serve as our line of this defense. In a system dominated by the clients, we need to be able to create a back pressure, and this is what multi-tenancy opens the door to protecting our own infrastructure from becoming overloaded or compromised. Many of these challenges are not unique to the monitoring world, but they might pose a unique challenge in the context of providing a Prometheus-enabled monitoring service. So based on our hypothetical service, we'll discuss this issue one by one. And the following should provide you with like a framework about how to think about these problems and their solutions once you start seeing them in your own practice. So let's talk a bit about hard and soft tenancy models. This is one of the initial questions we might ask ourselves, meaning how we can organize tenants within our instances. And as opposed to the traditional single-tenanted solution, we'll want to host multiple tenants within a single instance to decrease the overhead in both operational costs and resources. There can be an exception to this, where our organization might have a legitimate reason to opting for so-called hard tenancy for some users, where there might be a particular need to have a tenant exist in a completely isolated instance, and this might be to minimize any chance of disruptions from other tenants, or there could be, for example, a legal requirement where we might have to isolate tenants' data completely as well. The concept of shuffle sharding is also worth mentioning here, and this is a technique that minimizes the impact of outages or noisy neighbors on an instance in a soft tenancy scenario by limiting each tenant to a shard consisting of a subset of instances. And this feature is, for example, available in the Cortex or Mimir projects, so you can go and look it up for yourself. Authentication. We obviously want to know who our users are and whether they are who they claim to be in order to stop any unknown actors. So just like when it comes to securing other web applications, there is a host of solutions available. You might opt for a simple password-protected endpoint with basic auth. You might leverage MTLS and authenticate your users based on certificate information. For more complex use cases, you might need to reach for a more complete authentication built on top of a user management system. And to do this, you'll need kind of an identity provider, meaning an extra service that can manage identities on your behalf. Maybe your company has their own identity provider based, for example, on Keycloak, or you could use one of the existing solutions that you might be familiar with and that we also seen today, like Google, GitHub, Microsoft. And a popular choice to do this is to use the OpenID Connect protocol, which integrates also with the mentioned third-party providers and builds on top of the OAuth 2.0 authorization protocol. Obviously, one caveat with doing this is that you're now introducing an extra dependency between your client and yourself, and meaning that if the authentication, if the identity provider is down, you might also not be able to serve your own clients. Authorization. Once we know who our users are, we also want to make sure they are only entitled to do what we want them to do. So naturally, our tenants should be only able to read their own data and write data on behalf of their tenant, with the exception of the cross-tenant view, which we might cover later. And for some tenants, we might also want to limit the actions they might do. So for some tenants, it might be enough to just write data or read data. And even within a single tenant, there might be different types of users, right? So for some users, we might not require read permissions, such as might be the case with the Prometheus clients, remote writing to our service, where the read permission is redundant, so we can kind of tighten up those privileges and we can remove the read privilege. Again, for simple use cases, this could be kind of statically defined in a configuration file, or for more complex permission handling, you can look at the Open Policy Agent project, which is a policy engine that lets you define and enforce policies. Finally, we know who our tenants are, and we make sure they can do only what we want them to do. We also want to limit the quantity of their actions. As we already mentioned, hard tenancy and shuffle sharding can give us kind of a baseline solution, but also a good way of ensuring that our tenants are playing nicely is to use rate limiting in order to slow them down if they're using our service disproportionately. It's important to pay attention to both read and write path, as the tenants could obviously cause disruption on both paths. And when we're thinking about these limits, there are certain dimensions that can help us to guide our decision when setting the limits. So most naturally, you might want to limit the frequency of the request and respond with an appropriate error message and a code to tell the client to retry later. Or we can also pay attention to the size of the request and set a limit for the total size of the request, and make sure that we refuse to handle any kind of outliers from the beginning. Still, relying solely on frequency or row size of the request, it's not sophisticated and predictable enough, especially when in the Prometheus world we're dealing with series and samples. So here we can borrow some concepts from capacity planning and think about how much capacity we would want to provide to our tenants. And here active series can offer a good proxy for the number of series our tenant is currently using. But figuring how many active series a tenant has is also not trivial. Although this information can be inferred from the internal metrics of the Prometheus TSDB, in the distributed system, this information needs to be extracted from multiple instances of TSDB due to the nature of how things are handled, so there could be replication going on. And so we need to look at all of these TSDBs and calculate the active series based on metrics from all of these instances. One experimental approach we're trying at Thanos is to use what we call meta-monitoring approach, where we try to limit the number of series based on active series metrics from our whole Thanos deployment. And in a similar way, we should consider not only the active series, but we also should be looking at the potentially the number of labels and samples that your clients are sending you. Now, metering, similarly kind of to rate limiting, we'll also want to know how much of our service our tenants are using so that we can attribute our costs to them. And again, this is kind of a similar case to rate limiting. You might want to focus on the number of series and samples, again, our base units in the Prometheus world. And in this case, you should probably also not consider just the number of active series, but here also the long-term storage comes into play. So you should also consider the costs of long-term storage here.
Cool. So we've spoken about what mass is. We've spoken about how you would implement mass at quite a low level. And I guess what stands out to a lot of people is that it's a lot of stuff to have to worry about. It's a lot of stuff that you have to maintain. There's an option, which is you could pay someone to take care of it for you. So you could go find a third-party vendor like Grafana, like AWS, like Google, and they could take care of the problem for you. They're generally pretty easy to adopt. It's usually a line of config that you add to your Prometheus setup. And oftentimes these services include some form of SLAs, platform support, etc., which is nice if you don't want to hire engineers to have to do that. Oftentimes these services are paid by usage. Mate kind of touched on this metering problem and kind of tracking and limiting users. It's pretty hard with Prometheus. There are a lot of different things that a user can do when they interact with your system. So oftentimes they're kind of similar. A lot of them track active series that you write, but some will charge you by samples. Some will charge you for querying, some won't. Some will charge you for storage, persistent storage in the cloud. So it kind of varies. But with excessive use, as you're paying as you go, this can get very expensive. Moving metrics can also be difficult. Oftentimes when we adopt new and exciting technology, we don't really think about what it'd be like to unadopt it and use something else. So a lot of these services make it intentionally or unintentionally difficult to exfiltrate your data. So if you've been sending years of metrics to a particular place, and now you want to take those blocks or take that data out, it's sometimes tricky, or it can be expensive. There's also compliance. Not all of us work in industries where we can just publicly send telemetry and metrics out into the wild. Some of these vendors do offer on-premises solutions, so if you want to go with a commercial product, I recommend you talk to them. There are loads of representatives from those companies here today as well. And the second option is you could do it yourself. You could use open source software off the shelf, like Thanos, like Cortex, like Grafana Mimir, like Victoria Metrics. There are loads of Prometheus high availability persistent setups that you could adopt and deploy. But it is a challenge. It's not going to be easy. You're going to have to build context on these projects. You're going to have to run your own infrastructure. It's quite complex to configure some of these things because they're big distributed systems. And then you also have to pay for the compute. You have to pay for your Kubernetes cluster, your nodes. You have to pay for egress. You have to pay engineers to manage it. This is a non-trivial problem or non-trivial cost to doing this. But economies of scale, if you're consuming a lot of metrics, it might be worth it. You also have flexibility in your platform. You know where your data lives. You can change from Cortex to Thanos or Thanos to Mimir, however you would like. So you own your data, you own your infrastructure, you know where it is, you can run it in your own data centers if you're on-prem, etc. So this is kind of a matrix of some of the features we've spoken about today. Read limits, multi-tenancy support, monitoring, Auth-C, authentication. I won't go through all the details, but you can see that various projects are in different levels of maturity when it comes to features that you need to facilitate monitoring as a service. And that's where observability as a service comes, because we love our X as a service in this industry. Now, observability as a service is kind of one level up from monitoring as a service. It encompasses multiple signals, so it will encompass your tracing, logging, and potentially your metrics, and continuous profiling if you have something like that. And oftentimes these observability as a service open source projects are meta projects. They kind of glue everything together and they put it behind an opinionated, opaque single API. So when you're interacting with it, you don't actually know where your metrics are being persisted or how they're being persisted. You just care that they are being persisted. Also, you have the benefit of having universal tenants and authentication authorization across all of your signals, which could be a huge benefit if you're offering this to other teams within your company, for example. And they're extensible as well. You don't have to use a particular ingester. They're often opaque APIs. They're open source projects, so you can contribute to them and change them. Some examples of these are Obstrace, which GitLab use quite extensively. I know they're here today. There's Observatorium, which is what we use at Red Hat. And OpenTelemetry, kind of. It kind of offers the same thing. But it doesn't really give you an opinion on authentication authorization. Cool. So what's this going to cost me is perhaps a good question. Like I said at the beginning, oftentimes observability is something everybody wants a lot of. Everybody wants high-resolution data, traces on everything that isn't sampled, logs for everything that are persisted for a long period of time. But all of these things have cost. So what I'm going to briefly do is a comparison between kind of three of the top vendors of monitoring as a service, Grafana, Google, and AWS, and a comparative setup with Observatorium and Thanos that could handle about the same amount of time series. For the sake of example, we want to persist 10 million active series, and we want to scrape or write these metrics twice a minute, so once every 30 seconds. So the setup that I ran this on was Thanos and Observatorium. We used about 300 gigabytes of memory, 15 CPU. That was about 5 EC2 nodes. We used about 400 gig of disk. You have to pay for some egress. And then that's the topology if you want to look at it, how many replicas of everything I'm running. This doesn't account for, what I'm about to show you in the next slide, does not account for the Kubernetes master nodes as well. So your control plane, depending on how you've adopted your Kubernetes, you either pay for your control plane or not. You have to factor that usage in as well. You also have to factor in the fact that you'll have an engineer that's going to be maintaining this for people. So this is vaguely the comparison. So we have some amount of active series, some scrape interval, and that gives you your effective data points per minute. That's useful for some vendors, not useful for others. For the sake of example, I've used the public calculators for all of these services. And another example that I wanted to draw attention to was that negotiated rate that Grafana has. Obviously, knowing that there's Grafana here, we went and spoke to them. We were like, hey, if we were doing this use case, how much would it cost us? What would it look like? And oftentimes, if you're sending a high volume of metrics, they'll give you better rates. So definitely talk to them before you adopt anything. And then at the end, you can see what it would cost in compute cost. Obviously, this is an oversimplification of this problem. There are a lot of other costs that go into running it yourself. But again, for me, it's useful data to just understand what the cost benefit is, and more importantly, how this scales with usage. So the more usage you have, the decision of whether you should run it yourself or whether you should pay someone to run it might change as well. And I wanted to give a shout out to this Thanos blog as well, Thanos at Vidalia, where they managed to run a hybrid Thanos deployment that scaled to support a billion series across 40 data centers. The thing I kind of want to point out is I saw a lot of you use Prometheus, but not a lot of you use monitoring as a service. There is a trend in cloud native generally of people moving to multiple clusters, to regional clusters, to more complex topologies that might necessitate this. And we're seeing this reflected in Thanos with the features that people are working on and the importance of projects like Mimir and Victoria Metrics. Thank you, everyone. That's it.
Okay. Any questions? Anyone? No questions? Okay. Thank you very much. All right. Next up is James from Timescale.
You want clip on one? Yeah,
okay.
But I don't know if it takes too long.
Hello, can you hear me? Hello? Hi? Can you hear me? Ah, good, okay. Just give me a second to get set up here. Okay. Good afternoon. Hi, everyone. So my name is James Guthrie. I work at Timescale. I work on a product called PromQL. You may have heard of it before. You can probably tell by the name, it started its life as a Prometheus remote write storage backend, but nowadays it's kind of like becoming a storage backend for all sorts of observability data. So we store traces, we store metrics, and we're going to do more stuff in the future. But when we were looking into OpenTelemetry metrics, we kind of realized that there are some differences, and that was kind of how the idea for this talk came about. So before I really get into things, I kind of want to see what's going on in the audience about like what people actually know. So the previous talk, they asked how many people are using Prometheus in production. I saw a lot of hands go up. So how many people were aware that OpenTelemetry metrics became generally available earlier this year or late last year. Okay, so about a third of the audience. Okay, how many of those people spent some time to think about, like, okay, OpenTelemetry metrics, what am I going to do with this now? 5, maybe? Okay, how many people are actually running anything that uses OpenTelemetry metrics? 1. Okay, and how many people are using OpenTelemetry traces in their production setups? Okay, quite a few more, so about 15, I guess. Cool. So when it came to putting together this talk, I realized that OpenTelemetry metrics is kind of a jungle. There is a lot that one could talk about, and it would not fit into a 20-minute talk. So I had to kind of like try and find a path that goes through that jungle. And the point of view that I've chosen to take in this talk is, as you could see in the title, the operator's point of view. So I'm basically not really going to cover anything about how do I instrument my application, which SDKs do I use, how do I do all that stuff. I'm not going to talk about any of that at all. I'm basically going to talk about it from the point of view of if you are operating an existing Prometheus setup and somebody comes and says, hey, I have this thing, it's doing OpenTelemetry metrics, what are things that you need to kind of think about or care about? So a couple of the questions that I'm going to try and answer today are, what do I do with an app that's been instrumented with OpenTelemetry metrics? Can I just like plug this thing into what I already have? And what things do I need to kind of be aware of? So let's start with some easy things. First off, is OpenMetrics the same thing as OpenTelemetry metrics? I was at a conference a couple weeks ago, and somebody had this idea that, like, oh, you know, the name is kind of the same, it must be the same, right? The answer is no. They are not the same thing. So the next question you may wonder is, like, is there some sort of interoperability between these things? And the answer is yes. There's kind of been an explicit design goal of the OpenTelemetry metrics people to make Prometheus and OpenMetrics work with OpenTelemetry metrics. So they do interoperate well. So you may say then, okay, well, so there's nothing I need to worry about anymore? And the answer is, well, kinda, and that's why I'm here today. So let's start with something that you will know. This is kind of like also, again, the operator's point of view. This is how you will kind of see your world as with metric collection. So we've got a service on the left. It's exposing a Prometheus metrics endpoint. We've got a Prometheus in the middle. It's got a list of targets. It's scraping the targets. It's getting the metrics. And maybe we've heard a lot about different long-term storages. Maybe you're using remote write to write into a long-term storage. So what does this look like in the OpenTelemetry metrics world? Well, in OpenTelemetry metrics, we have our service. It's instrumented with the OpenTelemetry metrics client libraries. It's pushing data using this OTLP, the OpenTelemetry line protocol, which is their way of sending data, into a telemetry storage box. So I know you're seeing this, and the first thing that's going through your mind is, oh my God. Like, it's doing push. Like, the Holy Tome of Prometheus states, thou shalt pull thy metrics. And so we can't really do anything with this. And by the way, if you haven't received your Holy Tome of Prometheus yet, they'll be available at the end of the conference, together with the 7 cardinality sins. But anyway, back to business. So the fun thing about OpenTelemetry metrics is this box here, this telemetry storage box, it isn't really defined what it has to be able to do, aside from ingest metrics. So there's no API definition. There's no query language definition. There's a bunch of stuff that you would be used to having in the Prometheus world that you will just not have in this box, at least not by definition. And it's also kind of like not a goal of the OpenTelemetry project to standardize those things. They're not going to standardize APIs. They're not going to standardize query languages, or at least they don't want to for now. So what is this box in reality? Well, there are a bunch of vendors that want to be this box. That's kind of why OpenTelemetry exists in the first place, so you can have this interoperability between different vendors who are trying to provide services. So some well-known examples that you may be aware of are a pivoted dog dating service, collector of relics, people who like to step on lights, and some honeybees. So there's also a growing ecosystem of open source solutions around OpenTelemetry metrics, but none of them really will give you the features that you're used to out of the box with Prometheus. And I know that at KubeCon NA, Gautam had a talk basically on the same material as this. He mentioned that there are ideas in the Prometheus world of actually integrating OpenTelemetry line protocol so that Prometheus would be able to just receive OTLP metric data. Yeah, there were a couple of people in the audience who are familiar with traces. OTLP, you'll know that from there as well. It's kind of the same thing. So actually, there's one omission on this slide. Click. Oh. It works as a mouse pointer, so it's doing stuff on my screen now. There we go. OK. In reality, you'll actually set up your collection pipeline like this. So your application will push into this thing called a collector, and the collector will push into your storage backend. And actually, I kind of lie on this slide as well, because as far as the OpenTelemetry project is concerned, this is how metric collection works. So your service can be instrumented with OpenTelemetry, but it can also be instrumented with other things. It can push, but you can also do pull over here. You can have the collector pushing, or you could have pull from some sort of storage backend here, and the storage backend doesn't have to be OTLP. So there's a lot of flexibility in the model, which is cool, but also at times a little bit annoying. So I'd like to take a look at some of the different ways that you can configure and use the collector in setups that you may be familiar with. So this diagram we saw before. I didn't change anything. But now somebody comes along with their Snowflake service, and they say, hey, we did this thing, and we used OpenTelemetry metrics. Super cool, right? And you're like, well, but we used Prometheus here. So what can you do about this? Well, here you can basically plug in the collector as a sidecar. You have your service pushing OTLP metrics into the collector. The collector can expose a Prometheus-compatible text format exposition endpoint, and you can just configure your Prometheus to scrape from there. So problem solved. Now, maybe somebody else comes along and they're like, oh, so I've done a second service because the first one was so cool. So maybe you need to like promote this, this thing that was a sidecar into a service, and you can still scrape it from your Prometheus. And we can kind of take this a step further, and maybe you don't have any Prometheus services anymore, or instrumented with Prometheus, and you can have all your services pushing OTLP into the collector, and the collector can then remote write into your long-term Prometheus storage. And now somebody comes along, I don't know, from upper management, and they say, oh, we need to integrate with this external pivoted dog dating service, so we need to get all the data in there. Oh, wait, sorry, that was one slide too early. Yeah, we can go backwards as well. We can go back to a service which has Prometheus metrics, and we can scrape them from the collector and remote write them. And now comes the thing I was saying before. You can integrate your dating dog service via OTLP, as well as having remote write into your long-term storage. If there's anyone from Datadog here, please don't hate me. How does this work? So this diagram I lifted from the OpenTelemetry metrics, actually OpenTelemetry documentation. It's quite complicated. There are lots of boxes. But let's focus on the simple bits. So there's this vertical pillar here. This is called receivers. On the right, we have exporters. And in the middle, there are these processors. And basically, you can wire up your collector to kind of get data from different input sources. You can route them through different processors, and you can have them exported to different data sinks. So this green line, for instance, we're receiving OTLP data. It's going through some sort of batching and filtering, and then it's being stored in Prometheus in the end. So there are a ton of receivers, like 30 or 40, something like that. There are a couple for Prometheus, one for scrape, where basically you just configure it as you would your normal Prometheus, and it'll just scrape everything like Prometheus does. There's simple, which is intended to only scrape one target. There's OTLP, obviously. And then the interesting thing is that there are host metrics and Postgres. And one thing I didn't mention on the previous slide is this exporters thing. You guys know exporters from the Prometheus world is like this thing that you run next to your application and it exposes metrics. It's not the same thing here. They took the exporters term and they did something completely different with it. So not the same thing. But interestingly, or confusingly, the collector receivers do the same things that exporters do in the Prometheus world. So this host metrics receiver, for instance, is the same thing as the node exporter in the Prometheus world. It's a collector or a thing that basically will pick up metric data from the host that it's running on. And similarly for Postgres, you can have a receiver, which is basically connecting to a Postgres database and getting data out of it. There are also a bunch of exporters. There's Prometheus Scrape, which basically exposes a metrics endpoint in text format, remote write, we saw that before, OTLP, Elasticsearch, a bunch of other vendors. And there are a bunch of processors that you can use for batching, sampling, renaming, adding attributes, doing cumulative to delta conversion, which we'll see in a second what that's about. So far, so good. We've seen unicorns and rainbows. This is how we can connect all these different things together. Everything works beautifully. But does it? So there are some differences. There are differences in the metric data types, differences in naming conventions, differences in temporality, and differences in metric types. So let's go through these bit by bit, and we'll kind of like build up a picture of what's different and kind of what's the same, I guess. So the first thing is kind of a minor detail. OpenTelemetry metrics can be either floating point or integers. So you need to do conversion from integer to floating point in order to store them in Prometheus, which is probably not a problem most of the time. But if you get above a value above 2 to the power 53, then you start to lose precision in the numbers, and maybe that will mess with your life. Also, metrics always have an associated unit, and that unit is well defined. But what's interesting is that the semantics around the units are slightly different, or conventions around units are slightly different to how they are in Prometheus. There's a whole, because they're all standardized in OpenTelemetry metrics, there's a whole linked document of how you should use different unit types and so on and so forth. Basically, it's not necessarily the same as in Prometheus. So whereas Prometheus, you kind of like standardize on using seconds, in OpenTelemetry metrics, you can do kind of whatever you want. That brings us to naming conventions. So you may be familiar with this guy, Go memstats heap alloc bytes. This is a metric which is exposed by the Go runtime, how many bytes are allocated on the heap by the Go runtime at that point in time. So if you're scraping or getting metric data from a Go application, you'll be familiar with this. Now, in the OpenTelemetry world, obviously there is a Go client library that you can use to instrument your application, and will also expose a value which tells you what the allocated heap bytes are. But in OpenTelemetry metrics, this guy is called process.runtime.go.mem.heap.alloc with the unit of bytes. So the name is very different. And this name comes from these OTelemetric semantic conventions. I've linked the document here. It's interesting to go through and see kind of like how they see the world. It seems like kind of a nice way to look at things, but the bottom line is it's different. So one of the first things that you'll probably notice is, well, this name includes dots, and Prometheus metrics don't have dot names in them. There was an interesting discussion yesterday. Björn was saying how he wants to use dots to be able to do something in the PromQL language, and I also heard somewhere before that there was the idea of maybe allowing Prometheus to allow dots in the names. So these two conflicting ideas, I don't know, have to figure out what's going to end up happening there. But how is this dealt with in the exporters? Well, the exporters will do normalization. So the slide has got way too much text on it. So basically, the simple normalization will strip everything that isn't compatible and replace it with underscore. So we can go from process.runtime. To process_runtime_. And then there's an alpha level feature which you can activate in the exporter to do full normalization, which will kind of basically take a look at the underlying metric type and then append the unit at the end of the name because it knows what it is. But it won't do conversion from the different unit types. So if you have the unit as milliseconds, then it won't convert it to seconds for you because that's like the standard in Prometheus. At least not yet. Maybe that will be done at some point in the future. But now, an important point to note here is this process_runtime blah, blah, blah thing. This will be eaten by Prometheus, but none of your queries that you've written will work against it, right? Because you're used to using this guy, go memstats heap alloc bytes. So if you want to have your queries working, then you need to either rewrite your queries or do some sort of like renaming of the metrics as they go through, which kind of is a bit of a pain. So there's definitely some pain to be had there. Next is temporality. So OpenTelemetry metrics knows about cumulative and delta temporality. Now these are kind of like complicated names. Cumulative is basically what Prometheus does today, which is you start counting, basically, or keeping track of metrics, and as time goes by, you just keep on adding data that you collected, So if you have a new label that appears, then you'll keep track of that new label and all the old labels for a metric over time. What this means, though, is that the instrumentation client code is going to have state stored in approximately proportional to the cardinality of the labels in the application. Now, delta temporality is basically a thing where instead of keeping track of everything from the beginning of time, you kind of break it up into time intervals, and after each time interval, you forget everything that you had before, and you just sort of like transmit what you've seen so far. So here we can kind of like basically break the stream into this time bucket here, and we can send that data. Now, obviously, this is enabled by push. You can send that with push at your own desire to an external service, and then you can basically reset your counters to 0 and again, reset and count again. So what this means is that your client code basically ends up becoming stateless because you don't need to track all the state that you've seen over time, but it's only enabled by being able to do push. OK, so how is this dealt with in practice? In practice, the Prometheus exporter will accumulate delta metrics. So I didn't actually mention this, but when you instrument your code, you can choose to do it cumulative or delta. And so if the Prometheus exporter receives delta metrics, it will accumulate them, whereas the remote write exporter will basically say, delta, can't do this, drop it. There is no processor, which you would kind of maybe expect. Like you could just plug in a processor to the collector, and it would do the delta to cumulative conversion. That doesn't exist. But that's not because it's not wanted. There is an open issue. So if you feel like stepping back from your YAML, then maybe that would be something you could do. Finally, going to look at metric types. So I have quite a few slides on this, but at the end of the day, the amount of information is actually relatively small. So Prometheus has these 5 different metric types. Sparse histogram is new, yay. And for most metric types, there is compatibility or a path to compatibility between the OpenTelemetry metrics and the Prometheus metrics. But the names are slightly different. So we'll look at this from the point of view of the Prometheus metrics. In Prometheus, we have the counter. And there are 2 types which map from the OpenTelemetry world. They're both called sum. So OpenTelemetry has we saw this delta and cumulative. They also have the concept of monotonic and non-monotonic. So basically, monotonic is only increasing, and non-monotonic can be going up and down, like a gauge. But if you have delta and non-monotonic, it's kind of like a slightly different thing, where, for instance, if you had a queue, you can say, well, I know that I'm putting 2 items in this queue, and I know that I'm taking 3 items out of this queue, and you can actually keep track of those differences over time, which can help you to glean a little bit more information from the underlying thing than if you just had a counter which you kind of occasionally sample and see sort of what the current value is. Anywho, basically, the sum of a cumulative monotonic value is the same thing as a counter. So OpenTelemetry world, cumulative monotonic, same thing as a counter. A delta monotonic can be converted by basically adding up the deltas into a cumulative series, and that's the same thing as a counter. Then there's the gauge type. I said that there are cumulative non-monotonic. That's basically you can add positive and negative numbers to it, so it can go up and down like a gauge. They have this as a separate concept in OpenTelemetry metrics that maps to a gauge. And gauge also maps to a gauge. They have that type as well. There is a missing mapping, which is the sum of delta non-monotonic, which I kind of mentioned before. Those are not mappable. They'll be dropped. Yeah. So if any of your client applications actually use those, gone. Then histogram also has delta cumulative, can be mapped as well. Summary, I think, basically exists in OpenTelemetry metrics for compatibility with Prometheus, also exists, also mapping. Sparse histogram maps to exponential histogram. I mean, it can be mapped, but the sparse histogram or native histogram is so new that there's no actual mapping yet. But I think that, or I'm assuming that people are going to be working on this soon. So we began by asking, what can I do with an app instrumented with OTelemetrics? And can I just plug it into my existing Prometheus stack? And the answer is yes, basically you can. We also asked, what gotchas are there that I need to be aware of? And the answer is there are a few. We saw them. We didn't see them all. There were more. I couldn't cover them all. So just be aware that if you ever go down this path, you probably will stumble across a bunch of different things. And maybe you'll need to look for help from others that have been before you. If you'd like to do some more further reading on this topic, my colleague James Sewell wrote a couple of articles, one a deep dive into OTelemetrics, another Prometheus versus OTelemetrics. If you have any questions, I'm available. Thank you.
All right, questions going right here.
Hi, James. Thanks for the presentation. I guess my question is, a lot of the caveats, you did preface this by saying that kind of OpenTelemetry gives you portability with your metrics. But I guess in this particular case, if you were producing Prometheus metrics and then converting them into OpenTelemetry metrics and then writing them back to Prometheus, kind of what's a practical use case for that kind of additional step where you're going into something that's more abstract, that's not specific to Prometheus? And kind of a question that leads on from that is a lot of these third-party vendors accept remote write as a method of writing metrics to them. What are kind of the pros and cons of both approaches? Why would it be beneficial to pick one over the other? Thank you.
Okay. I think I can give a partial answer to that. One thing that can be a motivating use case for using OpenTelemetry metrics is having push. There are use cases where push is well suited to, and that are not very well suited to the existing Prometheus world. So for example, if you have IoT devices, things that want to have a small memory footprint, things that don't have continual access, that you don't have a continual access to because they don't expose an IP address, they're not on the internet or something like that. Or things like function as a service, or kind of like very lightweight services where they're very ephemeral. They just kind of, they come and go, but you don't really have control over them. That might be a use case where you would want to think of using the OpenTelemetry metrics pipeline just because it has delta. But aside from that, yeah, I mean, I think it's kind of having Prometheus and then kind of scraping that via the collector and then putting it back into Prometheus again, maybe not the smartest.
You mentioned a few different mappings between the two different types. Mm-hmm. Are there any other data types from OpenTelemetry that aren't mappable?
I don't believe so.
Anyone else? Hand up? No? Okay. So we're a bit ahead of schedule. Unless somebody comes and tells me otherwise, we got a break until quarter after. So thank you very much. Okay, we'll get started in a couple minutes. Just give everybody another second to trickle in. Okay, let's get started. Next up, we have Jaime from STIG, who's going to give us some information on fun with labels.
So, hello everyone. My name is Jaime Llera. I'm an integrations engineer at SysDig, and I'm also a maintainer of the open source project PromQL.io. Today, I'm here to talk about the different challenges that we can find with labels when we try to combine different metrics. I began to work at SysDig 5 months ago, and then I entered in this world of monitoring, where you can retrieve information from your application of your environments thanks to Prometheus metrics. I discovered that I could create these dashboards and alerts, and metrics give us that useful data to the users, and he can use it in a blink of an eye. So I thought, how can I do that? How can I turn all that metrics into that, in dashboards and alerts? And I began to work with PromQL. I was very excited, and I decided to build this huge combination of metrics, and in order to create these dashboards. And maybe I was very naive, because I thought that metrics were only a name and that was all, but obviously not. So I realized that behind of that metrics were the details that enrich metrics and give them all that powerful details and those dashboards with labels. I began to work with labels and discovered that all combination between my metrics should apply that and allocate those labels between my metrics. So for this talk, I prepare 3 different use cases, very basic, but very useful when you are beginning to work in this world with Prometheus metrics and its labels from scratch. So let's work with some math class with PromQL 101. And for this first example, when I begin to work with metrics and its combinations, I thought that I can enter in my Prometheus and tap my both metrics, and that will be enough. But that's not true, because when I try to recover the information from a simple combination, I just was in front of my screen with nothing on it. So after I realized that I had to combine my metrics using those labels, I began to see between this simple theoretical example and realize that I have some labels that matching between the metrics, and if I have a combination, this metric have to point and allocate those labels inside the syntax of my PromQL. And that is enough for the first sample, the first use case when you are working with PromQL. And for this one, this first example, I use this maybe different case instead of a simple one with two metrics, because obviously we have our rates and so many other operators, but in the basics, you have two different blocks and one operation between them. So I only have to have one time series. In this case, this summary of this rate at the beginning, and the other part, and only allocates the labels that we want to share between them. And obviously, there is a tiny difference, because in the first one, we have maybe in the first metric several labels that only a few of them can be in the other one, but maybe in another cases, we have the other example that most of the labels inside our first metric are in the second one, but we have to allocate the labels that's sharing, but we have to maybe erase a tiny part of the labels in one of them. So using another case, in this case, instead of onward, we use the ignoring. We select those labels that are different from the other part and apply the same syntax. And in this case, it's very simple, similar to the other one, but for a different context. The next use case I was thinking about is maybe a very simple one, but when you use it, give us some other details in your metric. In this case, maybe you are looking for a certain detail in your metrics, but you can find it because maybe when that metric was created, they can put that information inside that one, but we can take advantage of other information that we can recover for the cluster. In this case, with KCM, we can pick up info style metrics. This kind of metrics have a value of 0 or 1, depending on the metric, but we can take advantage of that, multiply or operate, in this case, with the metric, with the original one. And for example, if we are looking for some specific label for our metric, we want to aggregate this new label to the other one, only operate with this one, finding our label, in this case, I select in this theoretical example this one, and apply it in this group left. So we only have to select that specific label, apply a simple multiplication, in this case because the info style metric only takes the value of 1. We don't modify the original value of our metric, but we give that metric another detail and more information. So an example here, I decided to take this simple metric that have the CPU in this container. I couldn't find the URL name of the metric, so I decided to use this other info style metric, this called cute.info that came from KCM. And with this simple syntax, make a group left and take the information, making obviously the same use case, and the first one is matching the labels that combine between each other, and adding the new label. And just with that, we enrich our original metric. And for this case, for example, the third one, usually more of the supporters are creating but several people, and they are not maybe communicating with each other, and we have a standard for the metric, but there is no standard for labels, and maybe one people call one label in one way and other people call in another way, but the information inside the label is the same. So maybe we are thinking we can match those metrics because it has the same label in this case, but sometimes the difference could make us to no success in this operation. So we realize that we have some difference in the name of the label, and obviously we can match it in our operation. So we decided to make a simple label replace. In this theoretical example, I select the label replace before the operation, of course, because if I can match in those labels, we can return any information. It's very simple. You only have to select the original label that we want to modify, and the return, we select all with the regex expression and put all that information inside our new label. Obviously, this could help us with the simple example of some exporters have different name for one label to the other, but obviously we can create new labels with this use case because we can stack several label replace one on top of the other and take information from one label to the next one, and maybe we want to create some new label with the pod name, namespace, and container in the same label because reasons, and we have to take account this kind of use case. For this example, I take the other example in the second use case, but I select one because the label has the name created by name. Maybe for me it's not very logic because for me that is the workload. So I really have to apply this syntax for the example, and obviously you can see there the new label for the metric. So in order to summarize, labels give us the opportunity to filter our metrics, of course, because maybe we only want to pick information for certain pod or some namespace. Obviously, we can, without labels, we can match operations in this case. So as we said, as we saw in the first example, we had to match it. Obviously, we can enrich metrics with the information and the details in other metrics that give us another exporters. And obviously, we can change and create new labels with this simple syntax. But we can combine, of course, all this information and these PromQL and use cases. But obviously, when we begin with PromQL, like is in my case, I think we have to make baby steps and begin from the basics of this matter, for example, and I think this is the most important part. For me, it was very important to create this talk because I think there have to be more people in this world of monitoring. I think it's very important to create a community, and maybe some people are scared about some syntax or some technology, and this kind of talk could help us to introduce those people to this community. Thank you.
Hello. Okay. Any questions? Anyone at all? No? Okay. Thank you very much. Before the next talk, if anybody is interested, the sign-up sheet for Lightning Talks is outside in the hallway, and it will be taken down before the next talk starts or around that time. So if you want to, go sign up now. And next up, we'll have Richie, who's around somewhere. Ah, there he is.
I thought I would have 5 more minutes, so I need to finish one thing. If you didn't go out yet, we still have plenty of time for lightning talks. Also, I had a question earlier if non-Prometheus-specific lightning talks are okay. Basically, yes. If it's open source, if it's Go, if it's wider Prometheus ecosystem, if it's interesting to a tech audience, now is your chance. I also volunteered someone to make a lightning talk about the video setup here. And I'm just going to keep talking while I fix one last thing. If we were paying for GEMA licenses, we could actually have a nice song in the background, but we can't. Nee, möchte ich gerade noch nicht. Das ist voll okay, wir haben eine Viertelstunde Zeit. Okay. Yay. Okay, so this is going to be relatively short because it is initially, like, a few people canceled at the last minute, blah, 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 blah. Long story short, we didn't even plan to have this as a full talk. Thank you, Bartek, for putting me on stage. So yeah, this is an update on the Conformance program. Why do we want to have a Conformance program? Well, I don't have to convince this room that Prometheus is the de facto standard in cloud-native metric-based monitoring and has set the scene for basically the whole industry. We have hundreds of thousands of installations, millions of users. The market segment, which Prometheus defines as per Gartner and all those others, is literally billions and billions of revenue per year, which is quite a scary large number to think about. And at the core, it is really, really easy to say you are compatible. It's a lot harder to actually be compatible. In particular, when it comes down to the nitty-gritty details of how a specific function behaves or how that one value is returned. And it's hard for people to figure this out on their own, and it's hard for people to do the same research again and again, and then you have it through the grapevine. It's also simply unfair. So there might be confusion, sometimes deliberate, sometimes not deliberate, but in the end there is confusion. That is why we felt forced to go down this path. How this works? We have a repository where you have a set of tests which can be run against your implementation, against your cloud provider, by the cloud provider internally. We saw a little bit about this for the alert manager generator or alert generator compliance yesterday. And this is only half of it. Of course, like for us, the tech is interesting, but that's actually not the thing which really bites. So on the other side, CNCF, or to be more precise, the Linux Foundation, because CNCF is not really its own legal thing. It is the Linux Foundation, which is actually standing behind all of this, which also holds the trademarks. Like if you want to use the Prometheus trademark or so, you always end up at the Linux Foundation, not at the CNCF, which most people don't know. I just find it funny and amusing, or interesting to be precise. So the thing is, by introducing a new trademark, you can define who is allowed to use that trademark. For Prometheus, it's relatively easy. You can use it for descriptive use. You cannot say blah, blah, blah Prometheus or the blah, blah, blah Prometheus. You have to say blah, blah, blah for Prometheus. You can find all of this on the Linux Foundation trademark website and overview. The thing is, this is going to be a special trademark where companies or projects can sign paperwork with CNCF binding themselves to follow the guidelines of that certification program. Then they can self-test, submit results, and then they get a time-limited permission to use this mark. And then they need to keep it up to date. And the thing is, none of this is on the technical level. I mean, yes, the running of the tests is on the technical level, but the thing which the people at the companies who become part of this, they don't really have to care about that thing. What they actually care about is the license to use this trademark, which I find extremely amusing, to be honest, because it's like something which in the tech scene is usually not really seen as a positive, is used as a positive force and as a forcing function to get people to actually play by the rules and be honest about stuff. There are 3 names in the whole thing. This is a little bit confusing, but it is quite deliberate, because relatively early in the design process, we realized that even just us starting to talk about stuff, a few market players immediately got quite creative in how they were using words. Of course, again, those words are worth quite a bit of money. So basically, we decided to just hog all the words, so you can't play games, because those are now clearly well-defined within the scheme of the Conformance program. So once you've signed it, you can absolutely not play games with those anymore, because they are well-defined. So Conformance is the name of the program. Compliance is with a or more than one subsystems or APIs. And compatibility is the thing which people actually want to have. You can be compatible as an exporter or as a backend, or like there's different levels, because it doesn't make sense to require an agent to be able to send alerts, obviously. But the thing is, by using it in this way, we also block at least the nice terms from creative use. For end users, the only thing you need to care about is Prometheus compatible. It's going to look like, I forgot to put a picture in, but it's basically a little square thing with the Prometheus logo, and then it says Prometheus compatible, and then it tells you the component, like long-term storage, backend, agent, whatever. Why would people want to do this? Again, lots of money. But there's also other things at play once we hopefully unlock this within companies. Because usually the tech people at companies have a relatively or a really good understanding of what actually works and does not work. And even if they don't have it, having an official reference gives them the ability to self-test and to figure out if things are good. And also, a lot of time, people know what their competitors are doing, are not doing, where they are compatible, where they are not compatible. But you don't really want to talk like in the open market about like calling someone else's baby ugly is never a good move. But we hope that a few companies will be enticed to contribute more to Prometheus, maybe in the compliance area. So they add tests where they know that they are good, and maybe know that someone else is not quite as perfect. It's not the best of incentive structures, but history has shown CNCF that this is apparently quite effective. For the bean counters, the incentive is money. Our initial cadence is probably going to be quite aggressive. Of course, we still need to iterate on the thing, but as you can self-certify, the overhead is hopefully relatively little for the people who actually run through the thing. And if you want to have help convincing your manager, your company, your vendor, whatever, to take part in this, please let us know. We are more than happy to help. So, honestly, we are not where we want to be. This has been in the making for quite some time. There was a little bit of overwork on CNCF side that stopped some time ago. Then there was a little bit of overwork on my side. It's now back on track. What we need initially to launch this from CNCF side, like it's not a hard requirement, but they would like this, is to have 3 companies and/or projects which sign up initially. So at launch we can say, okay, those are the initially compatible ones. So it's not the case of, oh, only that one company made it. Like I have a pretty good idea about what company is 100% compatible, but we would like more. So if you work at a company, if you have a project, if you whatever, email Prometheus team, please, and get in touch, start running the tests against your stuff. We are more than happy to help you figure this stuff out. And yeah. But there's one more thing. While I don't have a black sweater, there's one more thing. And I'm a little bit, I'm halfway taking off my Prometheus hat and putting on my Grafana hat or my traditional PromCon hat. But I was saying, just plastering over earlier, we have hundreds of thousands of installations. And it's really, really hard to get good numbers. Like we have some mechanisms within Prometheus team, but it's really hard to get good numbers. If you've been around the PromCon for some time, you might know Carl Bergqvist, who's sadly not here today, but he always did this, where we saw over time how the adoption stats for Prometheus and Grafana were. Of course, Grafana has relatively good insight into those numbers, but also they're really valuable. So basically, those numbers are closely guarded and not giving out, except for at PromCon. Like that's literally the one place where we give, like we with the Grafana hat on, give out those numbers. So without much further ado, those are, as of today, the current adoption stats of both Grafana and Prometheus. And as you can see, I'm really bad at graphics, so I don't have this nice thing, which Carl can make, but I can only make this. That's it. Questions?
Anyone? Hands up?
Now's your chance.
Seems like no.
Okay.
No?
Then
Okay.
we get started with lightning talks early. So for lightning talks, same procedure, please. You still have a little bit of time, so you can write yourself in, and we can sync this upwards. Line up, and basically once one person is done, already come up, connect your stuff. Oh yeah, I see a few people starting to write. Perfect. So, first lightning talk speaker. I don't have the list here. Actually, I have the list. So I'm just going to switch over. I'm not the speaker anymore. I'm the impromptu MC. So, Carlos Adiero Cortes, Daniel Moore, Anshul Shindal, Harkishin, you're the first 4 if you could line up. Yep. Okay.
tendrás. Es como esta parte. ¿Dónde está? Vale. Ya le das a esto y ya te verás.
¿Dónde está?
Arriba, si le das ahí slides. ¿Tienes el ratón allá?
No lo sé.
Allá, slides.
Okay, can you hear me? Okay. Hi, I'm Carlos Avigo. I'm integration engineer in SysTick and also a PromCat IO maintainer. I work all day creating dashboards and alerts and using PromQL, and I want to show you in this talk how you can use Prometheus relabeling to make your life way easier. So in the first example, let's say we have a Kubernetes cluster and we want to deploy any kind of application that we want to monitor, any kind of application like a database or some application like Nginx. In this example, let's use Nginx. So we deploy Nginx with a Spotter and we do some Prometheus job, some simple dashboards, some simple alerts, and everything works fine. But then other teams start deploying their own engines in their own namespaces or even our own namespace. And we start also getting their metrics in our Grafana dashboards. And we don't want to say their metrics in our Grafana dashboards, nor we want to get an alert in the middle of the night from their pods. So we check we check the metrics to see if there is any kind of label that we can use to distinguish between their pods and our pods, but we don't think that we can use anything from there. So what can we do? With Prometheus relabeling and the Prometheus service discovery, we can get things from Kubernetes, like if our application or deployment or daemon set has any kind of annotation, any kind of label, we can take that and add it as a label in the Prometheus metrics. In fact, in addition to that, there are some kind of hidden annotations and hidden labels that we can also get from Kubernetes, like the meta Kubernetes namespace, the pod name, the container name. So if we add those to our Prometheus job, just a couple of lines there, we can add them as labels in our metrics. And now that our metrics have those labels, we can do some minor modifications in our Grafana dashboards or in our alerts, and then we can select only our engine pods and not other team pods. In fact, if we share this dashboard and alerts with the other teams, they can also use them too. In this lightning talk, we don't have time to see other hidden labels, these internal labels, or how to do these relabeling operations, but you have there two very useful links. One of them is the Prometheus documentation about service discovery, and the other one is a very good Grafana blog post about how this relabeling works with examples of all these operations. And in the next two examples, we are going to use also relabeling with Prometheus, but without the service discovery. In these examples, our metrics have labels that have very important information inside, and we want to extract that information from those labels. In the first example is from FluentD. I don't know if you know this open source project. It's an application that you can deploy as a demo set in your Kubernetes, and it will scrape logs from the other pods in Kubernetes, and then send those logs to other applications like, for example, Elasticsearch. Also, more precisely, these logs are not scraped directly from the pods. They are scraped from the log files in the Kubernetes nodes. So when we wanted to monitor FluentD, we saw some metric, some counter metric, which increased its value for every log that FluentD scraped from the other applications. And we wanted to correlate that number with the target. We wanted to see how many logs FluentD was scraping from Nginx, MySQL, MongoDB, and whatever. But if we use the Prometheus service discovery relabeling that we did before, we saw that those labels only had values from FluentD. We didn't get labels from Nginx or MongoDB. So nothing that we can do, right? luckily, there was a label in those metrics, which was, in this case, it was tag, which had a really long string, and that string was the name of the log file inside the Kubernetes node. And luckily, that log file contained the name of the pod, the name of the namespace, and the name of the container name. So we can extract those 3 pieces of information in our Prometheus job with some really long magical regex and add them as labels in our Prometheus metrics. So we add these 3 labels, and now that we have them, we add them to our Grafana dashboard and in our PromQL queries, and we can now easily see how many logs we are scraping with FluentD in each of those targets. And finally, last example, last slide, a similar case with some Azure exporter. In this case, we did 2 relabeling operations. One of them was that this exporter exported the metrics, and all the metrics had the same name. In this case, my own metric name. But inside the labels, we saw one label which was the aggregation and other label which was the real metric name. But we wanted to have something more intuitive, like Azure underscore the metric name underscore and the aggregation. So how we can do it? Super easy, barely inconvenience. We just take those 2 labels, we target the name, the label name, and with some small regex, we replace the name. And the other thing that we can do is you see up there is a label called resource ID, which contains the subscription, the resource groups, the providers, and the servers. We can, same as FluentD, we can extract those 4 pieces of information and add them as new labels right there. So it's really easy and really powerful. And that's all. As you can see, with some minor tweaks in your Prometheus job, you can make your life way easier when you work with the Grafana dashboard and alerts. Thank you very much.
Hi, my name is Daniel Moore, and I work at Red Hat as an engineering manager for the OpenShift monitoring team. You've already seen a couple of my teammates here on stage today, and there's also another one coming up in another lightning talk. So before I joined Red Hat, I've always worked on the end user side of monitoring. So the companies I've worked for, we've used projects like Prometheus, either directly from upstream or also through an enterprise agreement, and we were relying on enterprise support. When joining Red Hat, I then got the opportunity to look at this monitoring thing from a different perspective, from the perspective of selling it as part of a product. And this perspective I wanted to share a bit with you today. Some of these things won't be a lot surprising for many, but for me it was a good learning. So today we support Prometheus and all the projects around it, Prometheus Operator, Alert Manager, Thanos, deployments on thousands of clusters worldwide as part of our customers' OpenShift subscriptions. So our customers rely on us for fixing bugs, for supporting them in configuration when something goes wrong, and also for feature requests they have towards us, that we work on them and implement these things. But how do we actually deal with that? So there are, of course, many customers and many different use cases, many different varieties how this is deployed. So you already saw that picture once today in a talk by our friends from SysTick about OpenShift security. This is the monitoring stack currently, and I want you to focus more on the lower part here. This is the OpenShift specific operators, which kind of enable us to keep things or to reduce the complexity in configuration, to reduce the possibilities of things which can go wrong. So especially the cluster monitoring operator is kind of the thing which makes us able to keep things simple, which means it kind of creates an immutable deployment of the monitoring stack with an opinionated configuration, and this is kind of a meta operator making sure that when someone changes something in the deployment, it's reset again. So if you want to change something in the platform monitoring deployment, you kind of need to set the stack into an unmanaged mode and also then don't get support anymore for it. Right, but of course, this has drawbacks. As we all know, the world keeps becoming more and more complex. There are new use cases coming up. So in the time when our cluster monitoring operator was designed, it was mainly focused on mid-sized clusters, self-hosted deployments. But nowadays, also edge cases like very resource-constrained environments, the telco industry, which with really small clusters, then very extreme scale become more and more important, multi-cluster. Then we also have new delivery models. For example, Red Hat focuses a lot on managed services recently, where suddenly our customers are not external companies anymore, but internal SRE teams. So we need to support these kind of things. And what we're doing, there's not really a magic formula around that. In parallel, we try to add some flexibility to the existing stack, but also innovate on some new components. So I just wanted to give you a list of things we're currently working on in this regard, so that you can look up all of that. It's either on GitHub, in the official documentation of OpenShift, or in our issue tracker. So for example, a few things for the in-cluster stack, scrape profiles, where people will be able to select kind of a preset number of scrape targets. So for example, for a resource-constrained environment, you can only reduce your scrape targets to a minimal set, which is there then for scaling or something, or for the basic alerting. Prometheus agent mode support, we already heard about that today. Alert relabel configs, where you can adjust the predefined alerts in OpenShift. We can support customizing node exporter collectors in the future, so adding, removing collectors from our preset configuration. And then a few things outside of the in-cluster stack, observatorium-based Red Hat observability service, providing centralized observability, multi-cluster use cases, multi-tenancy use cases. You heard Moad and Mate talk about that today. And one new thing, the observability operator. I see this as a good potential for kind of the future for the in-cluster stack. So you can have a look at it. It's currently mainly built for our internal use cases, but it might have potential to be also used on customer clusters in the future. So that's it. This is my manager task to show this. So thank you.
Hi everyone, I'm Anshul. So it's a pretty long title. So this is a part of my work which I did at the Technical University of Munich as my PhD. Currently I'm working as a SRE at Argo, but this presentation does not have anything to do with the Argo AI. So I will go through all these terms over this 5 minutes. Let's see if I can explain what this title means to. So there are many serverless compute platforms. So in the, let's say in the public cloud provider, we have AWS Lambda, Google Cloud Functions, or Azure Functions, and IBM Cloud Functions. But there are also open source platforms like Apache OpenWhisk, OpenFast, and Knative, which are quite popular these days. But these serverless compute platforms are confined to the cloud provider. Like, let's say you have on the public cloud, or you can host it on your on-prem servers. But there is no such seamless deployment of functions or sending the invocation across the edge and the cloud. And another problem with these serverless compute platform is that there is no standardization of the compute metrics, like the monitoring metrics. Each platform has its own metrics, and if you have to compare across the platforms, you have to play around with them. So that's another problem. So that's where, as part of my PhD, I developed a framework, which I called this as a function delivery network. So it's a network of the multiple clusters, let's say like AWS Lambda, Google Cloud Functions, or you can have it on your private cloud cluster, which hosts like OpenWhisk or OpenFast. Then it could be also on the HPC nodes, FPGA devices, or edge devices. And the combination of all these clusters mixed together forms the network. And the function delivery network sends the function to the right cluster depending on various heuristics. Like, let's say, like latency, compute requirement, HPC nodes, or stuff like that. So as part of the FDN, the major issue for me was how can I manage these whole clusters? Because they are distributed across edge, cloud, public cloud. And I developed multiple tools to figure out how I can do it. And then I came across, let's say, Kubernetes. So why not use Kubernetes to manage all these things? So that's where I came across Virtual Kubelet. How many of you over here have heard of Virtual Kubelet? A few of them. And how many of you have used it? So I can give you a quick overview of what Virtual Kubelet is. So Virtual Kubelet gives the impression to the master node of the Kubernetes that there exists a node, but there is no node. It's like a virtual node. And you have to implement few APIs like create pod or create or delete pod into your Virtual Kubelet APIs to manage it. So that's where I use the Virtual Kubelet to manage my clusters. So instead of having a worker node over there are these serverless compute clusters spread across edge and the cloud. So you can see over here, I have an API within the Virtual Kubelet for the OpenWhisk, OpenFast, AWS Lambda, and the Google Cloud Functions. So this made it easier for me within the Kubernetes cluster to manage my functions. So I can just use the kubectl-based commands to create a pod, and they would automatically be created as a function in the respective cluster. Another major part for the federation across these clusters is to collect the metrics. So because I require metrics for sending the function to various clusters, and for that I need the monitoring system. And that's where I developed a sidecar, which is deployed along with the particular virtual node. Over here you can see I have a virtual node which is specific to the OpenWhisk or OpenFast, and then it pulls the metrics from the Prometheus servers deployed on each cluster. Like if it's an open source, if it's an on-prem cluster, like over here with the OpenFast, or it goes to the cloud functions and it gets the metrics from the Google Cloud Function monitoring system, or from the CloudWatch from the AWS Lambda. And then these metrics are pushed to the InfluxDB. I'm currently writing it these act as a exporter for the Prometheus over here, and then you can visualize in the Grafana. And in the end, you have multiple clusters. Each cluster has its particular respective Virtual Kubelet node in the FDN cluster, and they have the monitoring system which collects the metrics from them, push it to either Prometheus or InfluxDB, and then view it on the Grafana itself, and just see like that. So here is just an example. So you can see different clusters. I don't know if you can see there are different clusters underneath over here, and for different metrics for each of the function. To give you an insight, it's just a small 30-second video, if I can play it. So this is where I collect all the metrics from all the functions. So I'm choosing like over here the different functions, and then the different metrics from different clusters would show up all together. So you can easily compare them across each other. Yeah, that's all from my side. So I'm welcome for your feedback, contribution, or anything. So this is the GitHub link for this particular whole framework. And if you have any questions or anything, just send me an email or post it on the GitHub. Thank you.
I want to talk about a new feature in Prometheus, which is PromQL prettifier. Now, seeing this example, we have two cases of the same PromQL query. The one towards the top is the PromQL query with random indentation, and the one in the bottom is a standardized form of PromQL expression. This is what the PromQL prettier does. So why should you use PromQL prettifier, and what was the motivation behind this feature? The main motivation was to make PromQL queries easier to read and debug. Like in this example, the first case towards the top does not clearly convey what the query does. But in the second case, the query is much easier to understand. Prettifier expressions also helps to understand PromQL query execution flow. Like in this example, the query execution starts from here, then it executes this block, and then finally the entire query. Another thing is that prettier works as a way to standardize PromQL expressions. Now, based on my knowledge, there isn't any strict format for writing PromQL queries, but prettifying expressions does work as a way to implement a weak standard than writing PromQL queries which are completely randomized. For example, in this case, the first query is an output from the prettier, and the next queries are basically valid permutations of the one from the prettier. Now, this feature can also be utilized by PromQL-related tools like writing PromQL mixins, because now you can treat PromQL prettier as something like Go format for PromQL. So rules for PromQL prettier, or what defines the PromQL prettier's behavior. The first rule is that any expression that exceeds the maximum characters limit will be prettified. For example, see the case 1. Imagine that query is within the character limit, then that will not be prettified. But imagine if the case 2 exceeds the characters limit, and it will be split into multiple lines. The next rule is that if you have any aggregation with by or without after the aggregation expression, then that will be prettified to by before that expression. Then the third rule is to split any PromQL function if it exceeds the maximum characters limit. Like the case 1 from the previous example, imagine if it doesn't exceed the characters limit, and in that case we do not split into multiple lines. But in case 2, imagine if it exceeds the characters limit, then in that case we split that function into multiple lines. For complete rules on prettifier's behavior, please refer to the prettier rules files in the PromQL parser module. So how does all this work? Imagine if a query like this, and when it's passed to the Prometheus PromQL parser, then it converts something like this structure in the memory. Now, this query is passed down into the structure in this format. And when we start the prettifying process, we do the bottom-up approach, which basically means we start with the child, the leaf node, which is the metric name here. We prettify that and move to its parent, which is the rate. Then we prettify the rate and then move to its parent, which is the histogram quantile. And like this, the entire query is prettified. So what are the areas that needs improvement in prettifier? So the first is to preserve comments, and what it means is if you have a PromQL query which has comments and you prettify that, then the output from the prettier will not have comments in that query. This is because the parser today does not preserve the comment information in the AST, and hence it's a to-do. The next is to preserve the execution order in binary operations. And what it means is if you have a query like this, and today if you prettify this query, then you will get an output like this. But the aim is to get an output which is this one. And why? Because the modulo in PromQL operators has a higher precedence than plus and minus. And what that means is modulo will have more indentation than the rest too. And that's all I wanted to share about PromQL Pretty in this talk. Thank you very much.
Yeah, but it doesn't mirror preferences. So this is me doing chaos engineering already. No. Ah. Sorry about that. My name is Michael, and in the next 5 minutes I want to talk a little bit about chaos engineering and how it can help with Kubernetes observability. And before we dive in, the obvious question I was telling myself, getting asked, we need monitoring at some point, so availability monitoring, performance monitoring, identifying slow performance, and blocking deployments. We have so many things to understand, metrics, logs, even more. Do we need to understand everything to really have monitoring? So we really need focus. And one of the first things is like, okay, we have metrics. Within Kubernetes, we have service discovery. We know within Prometheus, we can use that. We can define alerts and service level objectives. And from there, we can iterate. Prometheus has a great UI. You can use dashboards in Grafana, for example, or look into Persis, which is a new dashboards as code development, dashboards as code project, which is in development right now. And it's all great. Even more with Prometheus and the Prometheus operator, we can use everything which comes in one package. And the great thing I really like about it, you get dashboards and alerting rules already out of the box. So the thing is, we see a lot of things. So we have cluster metrics, we have pod metrics, so many metrics actually. But what can we actually do with that? So defining service level objectives and alerts for them. It's really great. We want to see something. We want to do something because a threshold has been violated, a rule has been matched, notify the responsive persona or teams, have documentation for incidents, run books, and also have corrective actions and reduce the mean time to response. But how, like, what can we do? For alerting, we often need refinements and groupings, and also avoiding alert fatigue. So having too many alerts and ignoring everything isn't the solution. And well, we can break something, kill some pods, and see some alerts, which could be a great way, but I think manual work is a bug. So maybe there's a way to break something more in a fun way, which could be using kubedoom, for example, in Kubernetes, but it might not be applicable for the workspace or the workplace. So we want to simulate an incident, but simulating a production incident is really hard. And I thought, well, let's add automated chaos in order to trigger alerts and service level objectives, and then iterate on them and verify them. Which brings me to adding chaos engineering and within observability. And one of the tools within the CNCF ecosystem I found is Chaos Mesh, which allows you to fail Kubernetes or hosts, like the pods, the network, HTTP, time, DNS, because it's always a DNS problem. And it allows you to run so-called chaos experiments on like just once or continuously as a schedule, and you can see how the applications are behaving, how the cluster is behaving, and verify everything from there. And one of the things I thought of, like, what could be a scenario which you don't expect? So like, think of an application that leaks memory, but only when DNS is failing. Would you expect that? Probably not. And I wrote an application because I burned out as a developer of debugging such things in the past. And you can control that DNS chaos with Chaos Mesh, actually. So defining the type DNS chaos, returning NX domain in DNS, and only failing, for example, for specific patterns. Chaos Mesh allows you to preview the pods which are being injected. And after a while, when the chaos experiment is running, you can see that the container memory usage is actually going up. And with an SLO defined of 10 megabytes, for example, you can also then have alerts within Prometheus, see them in the alert manager, and verify that everything is working as expected. The thing which is helpful to take as an action is like the alert counts might be too much. Maybe grouping is needed. Additional context in alerts might be needed. Adding more focus in dashboards, like reducing the amount of visible data, and also having the goal of to immediately see what's important during an incident, because I don't have time at 5 a.m. to look up everything, and really reducing the mean time to response there. Now, this goes a little beyond metrics with chaos engineering and observability, so we have many observability data types, and the great thing is we have OpenTelemetry as well with the specification, and we have had some talks already around this. And one of the thoughts I had, well, we could also use chaos engineering with traces, for example, stress testing a specific node or pod, and then instrumenting the Nginx service, for example, and seeing that the request time are like exploding or going up over time. This is an interesting area to inspect in the future. So having confidence with everything, you should know the limits of chaos. So avoid chaos inception, like don't run everything at once and break everything, because it could harm existing workflows and teams. Use staging environments to prevent data loss at some point. And also think about that like chaos engineering doesn't solve all the reliability issues, but it can help bring new perspectives. So bring chaos into observability, verify all the alerts and service level objectives, iterate, and think about maybe combining machine learning with chaos engineering at some point. Yeah, that's about it. Thanks for attention. The slides are already up on my website, dnsmiche.at. Yeah, that's it.
All right. Yeah, hi, I'm Jan. I work for Red Hat, and today I want to share an experience we had around timestamp ingestion and the effects around all that. Yeah, so some quick history on that. I'm sure most of you know Prometheus can optionally ingest timestamps. That has been basically there forever. It's usually strongly recommended against. I'm sure everybody knows that. So I'm not really sure what the original motivation around this was, since nobody's supposed to use it anyway. That's how that looks in the text format. Yeah. After a while then, in 2019 actually, an option was added to Prometheus to just ignore these explicit timestamps. So, you know, it's nice, we can be in control, so all good. And in Prometheus 2.0, staleness was reworked, so, you know, it's much snappier than it used to be. But explicit timestamps or metrics with explicit timestamps were explicitly excluded from that. So you're still stuck with the times out after 5 minutes. And if you want to know the details about that, I recommend checking out Brian Brazil's talk on that. I have some links in the last slide. Right, so maybe quick show of hands. Who here ingests metrics with explicit timestamps? Okay, it's only like 3. Who here monitors Kubernetes? It's a bit more, okay. There should be more overlap because basically one of these niche use cases, right, is cAdvisor. cAdvisor collects metrics out of band, and at some point they noticed some problems with that and actually added these explicit timestamps. Yeah, cAdvisor does that for performance reasons, and it's one of the reasons why people would like to have a replacement for that. Anyway, when cAdvisor started exposing these timestamps in 0.33, we quickly started seeing some issues that looked like that. So this is a container metric for a pod. Where the container gets killed. So you can see these long overlaps there between those lines. This is the old school Prometheus staleness handling. So now, you know, if you start summing these up to sort of keep track of how much memory your pod uses, you can imagine that you get graphs where your pod uses much more memory than it's supposed to have. That's, of course, not ideal. So, you know, we just ignore these timestamps. We added this option, right? We get the nicer staleness handling. So problem solved, right? Well, not quite. If you use other aggregations that take into account time, like rate is the obvious one. There's a bunch of others too. You get other issues. So if you look at this graph, this is the CPU usage for a container that uses as much CPU as it can, but is limited to use exactly 1 core. So I think most of you would expect a straight line across this, but since we ingest these samples that have been taken with the delta from the actual scrape time, but we use the scrape time as the actual timestamp, rate no longer really is reliable. And of course, this was the original motivation for adding this in cAdvisor, to actually get better rates. So we should have expected that, I guess. So how do we get around that? I mean, fix the exporters, that's really, you know, unless you use push gateways. If your exporter does this, then it probably shouldn't. That's what Prometheus expects, and then you don't end up in these sort of situations. If you can't do that, you can also, you know, collect according to how you're going to use it. So do you want to aggregate instant vectors? Do you want to sum them up? Ignore the timestamps for the better staleness handling. If you want to use rate and all the others, do respect those timestamps. And of course, if you want both, just have both, you know. You can replicate scrape jobs. You can drop the metrics that you want, rename, you can drop the metrics that you don't want, rename a bunch of metrics, and then just purposefully use with the right timestamps or with the better timestamps for your use case. And that's actually what we ended up doing. Or there might be a third option, I'm not sure about that yet, but with the new out-of-order sample ingestion, we might actually be able to get the staleness handling for explicit timestamps now, I think. So I'll create an issue, look for that, and then maybe we finally can have our cake and eat it too. And here's the links I promised, and that's it. Thank you.
Hi. Okay, so hi, my name is Fabian. I work at Grafana and I am maintainer of the official Prometheus Java metrics library. And in this talk I want to talk about a few breaking changes I have in mind, little disclaimers. So this is nothing that has been decided. It's not even consensus in any Prometheus team or so. It's really just my ideas, and I'm looking for feedback. So there is one thing that's actually a fact, which is there will be breaking changes when we implement native histograms in the Prometheus Java client. And the reason is that the current implementation is heavily based on this open metrics text format, which we see here. And this text format has like one value per metric. And if you look at the corresponding Java code, how it is implemented, it's exactly the same structure. It's also one value per metric. And as Björn laid out yesterday in his talk, with native histograms, we will have other types of metrics where a sample does not have one value, but a histogram as a value. So we need to change that, and that's pretty much at the core of the implementation. And so basically, what we have is two options. We can kind of take the blue pill and maybe have a little workaround for native histograms and then pretend that nothing evil happened and move on with mostly the current implementation. But we could also take this as an opportunity to refactor a lot of things that maybe are worthwhile refactoring. And as we are not even version 1.0 yet, it's actually a good point in time to do this now and then release 1.0. And what do I have in mind? How could a refactored implementation look like? So at its core, I would like to implement a Java module with the Prometheus metrics model. And like this is a read-only model for snapshots, a snapshot of a histogram, a snapshot of a counter, and so forth. And this will not be aligned with how open metrics text format looks. It will not be generated from protobuf. It will be really something that works well as Java classes, as simple as possible as you would implement it in Java. And then we would have a metrics library, of course, implementing the core metrics types. And when the Prometheus server scrapes, then this metric library would produce snapshots as defined in this data model, right? And then we could have modules for taking the data model and exposing it in different formats. We would, of course, use the text format, which is what everybody's using right now. We will have a module for protobuf, because native histograms aren't available in text format, so you need protobuf for that. And if we have such a generic thing, we could easily have another exporter module that exports Prometheus metrics in OpenTelemetry format, for example, right? But just to be clear, so the intention is not to be kind of a generic metrics framework for everything. The intention is to be a specific, Prometheus metric model implementation, but just with different ways to expose the Prometheus metrics, right? And then, of course, in the Java ecosystem, there are other metric libraries. There are also others that have a lot more adoption than the Prometheus metrics library. But what I think would be good for the ecosystem is like that other metrics libraries could reuse the stuff that's in this box here. So if you have another metrics library but want to support exporting to Prometheus, you could basically use the Prometheus metrics model as a dependency, produce snapshots in this Prometheus metrics model format, and then you could reuse these modules producing text format of it or producing Prometheus protobuf of it and so forth. So maybe it would be something that gets adopted by other implementers of metric libraries in the Java ecosystem. There are a couple of other things I have in mind. So mainly this package structure doesn't really work with how restrictions in modern Java version and so forth. So a little bit, moving back and forth, but it's maybe too much for a lightning talk. Now, one important message, if I do this, I will certainly implement something like a Prometheus simple client shim that implements most of the current API and then is backed by the new implementation so that you just don't need to rewrite all your instrumentation, but you can use the shim unless you use anything really weird and specific, and then you have time to migrate. So that's my ideas. If you have any feedback, you find me on the CNCF Slack, on the Grafana Slack, on Twitter, wherever, email, GitHub. Reach out, and yeah, thank you.
Thank you. There we go. Hi. My name is Alberto. I'm working at the observability team at Amadeus. So I had the idea of this talk after the presentation of Brian yesterday regarding the memory consumption in Prometheus. And one of the outcomes of this talk was you can look at this TSDB status page to look at which label consumes the more memory, and maybe you can label drop these labels. I have one problem is I will have to open thousands of TSDB status page. I don't want to do that. So yeah, we already faced this issue. And I love metrics. So to me, this web page was exposing some metrics. So I created last year a feature proposal to know if it would be accepted to expose all these stats as metrics. And it got rejected, mostly for two reasons. The first one is we're here at the close limit about best practices regarding cardinality and label value leaks, because this page only displays the top 10, so if it's switched, etc., you can have leaks, etc. The second reason is we have an easy workaround, and this workaround was proposed by Julien Pivotto, so thanks to him. This web page is also exposed in the API as JSON values, and in the community we have the JSON exporter, where you can basically JSON query the path and translate to metrics. So with a bit of configuration and a sidecar component to our Prometheus deployment, we are able to expose the status page as metrics. And so I'm able in Grafana to, let's say, rebuild this UI, and with the drop-down selector I can easily switch to my Prometheus, and I can even get which Prometheus instance are the well, wasting so much memory. Also, the good thing is you can graph these over time. So if your Prometheus memory go crazy, maybe you want to have a look at this dashboard to check if a new label like starting to consume a lot of memory. Yep, that's it for me. The config file for the JSON exporter is available in the feature request of Prometheus, so that's the issue number. And yep, thank you.
Yeah, great. Hello everyone, my name is Augustin. I'm working at Amadeus with Alban in the same team. I'm also a Prometheus team member, and I'm mainly focusing on how we can improve the Prometheus UI. For example, I am the one that created the PromQL editor we all love today. And today I will talk about Persys, that already spoken by Michael, but thank you for the heads up. So Persys, like Michael said, is a dashboard tooling, mainly focusing on GitOps oriented. Today it belongs to the Linux Foundation. It's sponsored by Amadeus and Chronosphere. Thank you, by the way, to Chronosphere to help us to build this tool. And the goal of this new tool is to explore how we can make a standard of the dashboard, of the dashboard format. And the goal is to go to the CNCF and to be part of the landscape as the monitoring ecosystem that you can find in the CNCF landscape. We have different objectives. The first one is to be compatible with, well, to provide a display for Prometheus first, because we want to display metrics in a simple and yet powerful way, and also because we just love Prometheus, so why not starting with Prometheus. Like I said, we want to be GitOps friendly, which means different things. First one, we want to be able to validate statically the dashboard format. So for that, we are providing a CLI and Q schemas, and with both the CLI and the Q schema, we are able to validate the dashboard format, which will be useful if you want to go on dashboard as code and validate what you are doing in a CI/CD. Later, we want to deploy the dashboard in the namespace along with your application using the custom resources. And also, we found it cool that, okay, you can edit your dashboard in a JSON and validate using the CI/CD, but well, when you are creating a huge dashboard with thousands of different panels, it's not anymore so funny to edit a JSON. So the idea is that you can run Persys locally super easily, edit your JSON file, and then store it back in Git. We want something embeddable. What does it mean? It means, well, if you analyze a bit the ecosystem in the monitoring area, you have Prometheus, you have Thanos, you have today now PromLens, and Persys in the future that want to display the same thing, which means time series in a graph. And we thought a bit about that, and we said, okay, well, at least on my side, that means we have 4 different UI to maintain. Why not creating one single time series chart and provide it to every UI that want to display the metrics? So that's an idea. We don't know yet if it will work, but we are working on that. So we might use these packages. Well, in Persys we are providing a different number of packages, NPM packages that we might be used in Prometheus to improve the graph display, and why not in a far, far future, why not displaying a direct dashboard in Prometheus or in Thomas? Let's see. As the status is an alpha version, so if you want to try it, be careful. It's we missed some feature, and you have not so much documentation. And I can show you a quick demo instead of talking in the void. Yeah. All right. It's looking like that. So you have some different panels. We only support for the moment 4 kinds of panels: the Go chart, the stat chart, the time series chart, and a markdown chart as well. We are currently working on the edit functionality, so not everything is working. For example, if I'm editing the Go chart, you only have the JSON format, but soon we will have a proper forms. Voilà. As a quick demo, really quick demo, I will go back to the status. What will come next? Of course, we'll write a lot of documentation that might be useful. We will support dashboard as code through CRDs. Maybe as a next data source support, we will support the traces. We need a logo. We need a lot of work. And perhaps integrate the line chart in Prometheus. Thank you very much. If you are interested, there is a link there. We have a chat in Matrix and the documentation to contribute. Thank you very much.
Hi there, I'm Moritz, DevOps engineer at Continental, but today is not about work. I want to talk about 3 things. This is a small Bluetooth sensor by Xiaomi. This is a small microcontroller, ESP32, and this is Prometheus. So I was a little bit too lazy to actually make slides, but I did a blog post, iptizer.medium.com, and I will just walk you through this. So what's the objective? Rising gas prices, stuff like that. So I was curious, what's the temperature in my flat at home? But I didn't want one sensor. I wanted 2 in each room, 1 on the left side, 1 on the right side, so a couple of sensors. And I also did not want to spend too much money, and I did want to do something with Prometheus. So, logical idea, take these sensors. It's 5 each or something, €5. ESP32, €4, I don't know. Stitch them all together with Prometheus. So, few lessons learned. So everything is quite basic. It's super easy. So if you have the hardware, it's probably 1 hour and you're ready to go. Setup is as follows: Prometheus scraping this ESP microcontroller and the microcontroller gathering via Bluetooth from this sensor. So first step. So there's the prerequisites. First step, I recommend to flash a custom firmware. Flashing a custom firmware can be tricky, but it's not in this case. Actually, just take your mobile phone. There's a static page, a static web page, and you can just flash it via Bluetooth. Super easy. 5 minutes or something, then you go, ready to go. Then microcontroller. I studied technical computer science, and yeah, this is not required in this case. So there is a project called ESP Home, and with all this, you can basically configure your microcontroller to log into Wi-Fi. So for PromCon Wi-Fi, you can have a web server with basic auth, and with the Prometheus, so this line here, you just activate Prometheus metrics there, and then there's the /metrics route available, and then you have the custom firmware which is PVXX. By the way, the guy that did this firmware hack, gotta watch this. I added the link there, crazy guy. Good. Then you have basically the sensor and the Mac, and then you're ready to go. You just flash it, whoop, and then that's basically it. You have your metrics there, Prometheus style, and probably don't tell you, scrape config, that's it. And then you're ready to go. You have your graph, you have your metrics. Yeah, you can read a lot. Actually, fun fact, so the blue one is my flat in Regensburg, and the other one is the old here in Munich, so it's cold. Yeah, that's it, basically. And by the way, there is now a Telegram alerting, so you could, for example, just alert on temperature drops or high humidity or something like that. So, thank you.
Mic check. Okay, cool. And go. So, hello everyone. My name is Claudio. I'm a software engineer at SIGUP. And today I want to borrow 5 of your minutes to talk to you about something that's not about observability, metrics, and whatsoever. This is actually a little project that I started this summer while on vacation, because of course that's how developers have fun. And it's basically born out of the experience I gathered over the years. I'm more of a developer than an ops person. So I had the chance to work with like web products, portals, applications in B2B and B2C. And you know, with the advent of microservices, or sort of microservices, so when we start to break the monoliths down, the pattern that we sort of like had to deal with was having multiple services. Maybe some projects had more, some had less, but the pattern there was an increasing number of services with maybe the same kind of problems and maintenance issues, such as like makefiles or CI pipelines, or I don't know, you name it, all the configurations that come with projects. And especially when you have, for example, multiple Go projects, so to speak, but it's not necessarily bound to a technology. The more you have, the higher the cost of keeping them in sync, assuming that's something you'd like to have, which I do because I have a little OCD. So lots of projects, lots of repeated stuff, little solutions to deal with that, at least to my understanding. So that sort of had me try to scratch that itch that is exactly that, right? And that's why I created Go Architect. It's an attempt. It's a very new project, so it's like 0.1 release, and I just started to create the basics, like the scaffolding for the future. Now we'll see in a bit what is that. And the inspiration for this project came from another project that in the PHP ecosystem called PHP Architect, which in turn was inspired by another project in the Java ecosystem called Arch Unit. And they're both aimed at testing your architectural constraints. So think static analysis, but with your own rules that act upon your code, okay? Since I started from I started speaking about makefiles and CI and stuff, that's only part of the story. There's also code architecture. So there's the two sides, the project architecture and then the code architecture. So I started from files because it was the easiest point of access. And I created this tool that is able to parse YAML files where we can specify matchers with their own set of rules. The inspiration comes also a little bit from like the BDD and spec kind of testing, where we have, in this case, like a matcher for files that matches all kind of files that end with a specific suffix. In this case, it's tool versions because it's like the ASDF tool that I'm targeting in this example that does not live within the root path, and it must contain a certain string. It should contain others. What does must or should mean? Well, if the rules say you must have like a Golang string within the file, then if the rule is not respected, the tool will fail. Otherwise, it's just issue a warning or an info depending on the level you want to enforce. And this YAML file can be validated through a schema that's part of Go Architect, and the tool is able to output text or JSON output, depending on maybe you need to parse with machine what the tool validates. It can loop through different files, like multiple configuration files, so you could sort of split and reuse maybe some rule files. And at the moment, as I said, it can like work on top of files and directories, which is just the very beginning. But in the future, I would like to integrate it with like other tools such as Comtest, or integrate it further with the like Golang parsers, so that you can inspect your code and define rules. For example, that, I don't know, some packages cannot import other packages in a stricter way than just the Go compiler allows you to do, or define conventions for name of the structures or interfaces and so on and so forth. And maybe also define some project templates that you can validate your microservices against, so that you don't have to create rules specifically for each and every file in your project and stuff like that. So this is still very, very early days of the project, but I would like to also ask for feedback and use cases, ideas. If you think this thing could help you in your job, or if you just have some anything to say, you can just head over Go Architect on Go for Slack, or post an issue on GitHub, and that would be super cool. And yeah, this is the link to the GitHub project, and that's it. Thank you.
One second.
Okay. Hi, everyone. I'm Tom. I'm working for Grafana Labs. And today I'm going to talk about MQTT and Prometheus. So just as a quick check, who knows what MQTT is? Oh, wow. That's more than expected. Cool. Yeah, for everyone else, basically, it's a message broker protocol, like publish-subscribe thing, which is supported by tons of IoT devices and some other use cases. It's basically like a group chat. Architecture-wise, it would work roughly the following. You have a client which publishes things to a broker, who then relays that message to other clients who have told the broker their interest in beforehand. And especially an open source firmware called Tasmota for tons of small battery powered devices supports this protocol. And I thought it would be super interesting to have these telemetry data in Prometheus. However, Prometheus obviously does not speak this protocol natively. So I came up with a scrape proxy, basically, to support this protocol. It's not a traditional exporter that it is statically configured, but inspired by the SNMP one, where you basically enter whatever you want to scrape as the target and then use relabel rules to make it go through the exporter. Basically, what happens here is that in the scrape config, I hope one can read this, you tell it the topic of your MQTT broker you want to scrape, and then using those relabel rules redirect it to the actual instance of this PromQTT tool, so that in Prometheus afterwards you still get like the instance correctly set to what you wanted to scrape. It has two modes of operation. The one is when your device is actually publishing float data to the broker. You can obviously just use that the way it is. The other one, which is more common, is when you get, like, for example, this massive JSON message. You can't just like convert that to a meaningful Prometheus metric because it needs some parsing. For the moment, this only works using regular expression capture groups, but this has proved fairly flexible. Like, it's not universal, but as long as your format stays roughly the same, this will work. This is an example for specific Tasmota where I use it to monitor the energy usage of tons of devices in my home, like using $5 plugs I put between devices and the main power outlet. Using some relabeling, I do get these metrics, which obviously look horrible, so I need to also rename them, which all happens in the Prometheus YAML. The exporter itself does not need to be reconfigured or restarted when you want to do this. And I end up with these. That's it. So in case you ever want to do it, that's a way to go. I'm sure there are others, and it lives on GitHub under my name called PromQTT. So feel free to try it out.
Hello, my name is Jan Wedershofen. I'm a sysadmin at SpaceNet. My main job is to build high available Proxmox clouds and managing it. Our monitoring software is Prometheus, so this is one point. This is one of the main points why I'm here. The other thing is you've maybe seen me running around with camera or without a camera. I'm doing the live streaming stuff here. Since this is a very spontaneous talk, I've just brought some pictures of our front of house desk up there. So you can see me just taking some pictures. My job here was to get your guys' presentation on a stream on YouTube, so everyone who couldn't come here can watch it online or watch the recording. So it's a kind of mess up there. Here, this is our main desk. From here we can control all the lighting, sound and video. And so you can see Basti Schubert, one of my colleagues. up there changing graphics. And here you can see the brains of the operations. So on the left, there's a laptop running OBS, which is providing graphics, animation for the projector back here. And on the right is my favorite pieces of equipment. It's a Blackmagic ATEM Mini. It's like OBS, so Open Broadcast Streaming Software, just in hardware. So I brought a close-up of it. You can put in 8 different inputs, and there are a lot of buttons. A couple of them do the same thing, and you can switch between inputs and record everything, stream it to YouTube, Twitch, Facebook, to anything which can accept RTMP. And you can also plug it in via USB-C to use it as a webcam for something like Teams. Here you can see my view of the world. So every input is listed on this control monitor. You can select graphics, videos, and switch it. And yeah, this was the easy part. So you can watch a YouTube tutorial. It takes 5 to 10 minutes, and you know it, and can do live streaming. But the hard part here in PromCon was image generating. So I brought some images like this one, or especially this one. Those are the graphics rendered in a live stream. So every speaker has its own graphic with name, presentation, company. So in a larger box you have your PowerPoint, and a smaller one your camera back there in the audience. The main problem was here, it felt like every 5 minutes the list who speaks has changed. So we don't want it to get in every 5 minutes to get the list, put it in Photoshop, and render new images. So there's a script. I haven't seen that you can automate Photoshop, so I found a script. You can take all of your input, like I've brought a Google spreadsheet with all your talks, and we created a spreadsheet, put it in a CSV file, merged it with this script, and Photoshop generated those images. And yeah, that's it. Thank you for attention.
He didn't even mention he's a first-time speaker, so extra round of applause. It's been a lot. So, thank yous. First of all, thank you to our sponsors. And if you've seen this before, as you're being called up, just come on stage. So thank you to all the speakers. Come up. I see more speakers who are not coming up. Hop, hop, hop. Also gives me some time to recover. Ja, das ist jetzt so. I know a few people already left for their planes and such, so we don't have the full roster, but to all MCs, I think we already have them on stage, but if not, then also please come on stage. To our Prometheus team members and maintainers, there's one missing. Okay, so wait, no. So to all the people who did the video and the network and the everything and the build-up. Good morning. And finally, thank all of you. So yeah, the last 5 years, I think 7 or 8 PromCons and Prometheus days and everything, has been a lot. Next year, it's in Berlin and I'm not leading it. Yes! Well, so yeah, they're going to do it. It's fine. Yeah, that's it. Be excellent to each other. If there's any trash, please take it out. I put a trash can at the exit, so you can just drop it there. Thank you.
Thank you, Richie.
Thank you, Richie.
Und dann noch mal auf das Rote. No.
Yeah? Oh, yeah. It would be so great if we could have it.
Sure.
Yeah.